Hello, everyone, and welcome to the first live session inaugurating the first International Electronic Conference on Actuator Technology, Materials, Devices, and Applications. This conference has been organized by MDPI and the journal Actuators. I would like to take this chance to thank our chairs and all the people from the conference committee for making this conference possible, and all the participants for joining us today. Just as a reminder, during this week and until Friday 27, you will be able to assist to several live sessions with excellent speakers and have the opportunity to read and comment all the author submissions presented for the conference. So please look at our webpage during this week for more updates and register for free for the following live sessions. I would like to remind everyone that this webinar is being recorded and that we also have a YouTube streaming today. The recording will be posted on the conference webpage for everyone to watch it as soon as possible, and I will be sharing the YouTube link through the chat in a few moments. I will now present our chairs. First, we have Professor José Luis Sánchez Rojas from the University of Castilla-La Mancha in Spain. His research interests cover optical and electrical characterization and modeling of semiconductor devices, miniaturization, design and application of MEMS and NEMS, and sensors and actuators. Our second chair is Professor Tatiana from Tampere University in Finland. She is an expert in electrohydrostatic systems and actuators, and cylinder sensorless position motion control, simulation, energy balance, and energy recovery system in off-road mobile machinery. Thank you both for accepting to participate in the session. The microphone is yours, so everyone enjoy.
Thank you, Anna. Thank you for the kind introduction, and welcome again to the International Electronic Conference on Actuator Technology, IeCAT 2020. As Anna said, my name is José Luis Sánchez Rojas, and I am professor of electronics at the University of La Mancha, right in the center of Spain. We have a beautiful sunny day today, but anyway, this is a virtual conference, so we have to limit ourselves to the technical aspects. I would like to introduce also to let the microphone to Tatiana, who is now with us.
Hello, my name is Tatiana Minav. I'm professor in hybrid rice in Tampere University, Finland. And we do have rain, but we had a snow. But we're honored to be chairs of this first edition of the conference, which is organized online by MDPE.
Okay, thank you. So I would like to thank you all for participating in the conference, and I hope you enjoyed the technical program that we have prepared with both live webinars and regular sessions with online presentations.
Today we will start with first session, Soft Biohybrid Actuation, will be chaired by Dr. Aslan Miriyev from Empa, Swiss Federal Laboratories for Material Science and Technology in Switzerland.
Okay, so Aslan, thank you for chairing the session, and the floor is yours. Enjoy.
Thank you very much. Thank you very much for a kind presentation. Good time of the day to everyone. Welcome, and thank you for being here. I'd like to thank the conference chairs, the conference committee, secretariat, and the organizing team. There has been a demand for a dissemination and discussion platform for actuation research. And I'm thankful to the organizers for their efforts to create this event. This is the first online conference platform that is fully dedicated to actuation. Today, we're celebrating the soft and biohybrid actuation session. And this emerging and fast developing domain, it involves talented scientists and engineers creating fascinating research. These days, soft actuation domain focuses mainly on leveraging the properties of the synthetic and biological matter into robotic functionality. We'll hear 6 talks, including the keynote lecture on shape memory alloys, followed by 2 invited talks on Biohybrid Actuation. And after a short break, we'll listen to 3 invited talks on the synthesis, implementation, and modeling of soft material actuators. I'd like to encourage all the participants to prepare their questions for the speakers. For your convenience, I'm sharing here on the chat the link to the Slido application, where you can easily type a question, and I will monitor Slido and will do my best to deliver your question to the speaker. I'm delighted to invite our keynote speaker, Professor Carmel Majidi from Carnegie Mellon University in the United States, to give a talk on untethered soft robots with shape memory actuators. Please, Professor Majidi.
So thank you very much, Aslan. Really excited to be here, and thanks so much for organizing this session. Very exciting topic, and really excited to see the rest of the talks. Also, thank you to the conference organizers. So my name is Carmel Majidi. I'm Clarence H. Adamson Professor of Mechanical Engineering at Carnegie Mellon University. I lead the Soft Machines Lab, and I'll be presenting work from my group on using shape memory materials for applications in soft robotics. So just kind of taking a step back, kind of more generally in terms of, what is soft robotics and why it is important in a lot of emerging applications. Well, robotics more generally are completely phenomenal for what they're designed to do. They're indispensable tools in a factory or a heavy-duty manufacturing setting, but the same power and bulk that make these so amazing in manufacturing make them quite dangerous, say, in a domestic setting. And so that's motivated engineers and roboticists over the decades to build soft, lightweight, and human-safe counterparts to these bulkier machines. I think of Joe McKibben as being one of the early pioneers of this field of soft robotics back in the 1950s. He built a soft robot hand exoskeleton for his daughter, Karen, who was suffering from polio. Now, the actuator that he used is a pneumatic actuator. Sometimes we call this a McKibben actuator, although it had been previously discovered by a French inventor named Henry Morin. This is a kind of a modern day version of that pneumatic air muscle, where the architecture is quite simple, but incredibly effective. Compressed air being used to cause contraction of this actuator in a manner somewhat analogous to contraction of natural muscle, where you get both shape change, but also a stiffening effect. Over the decades after, there's been steady progress in the field of soft robotics. So again, starting with that soft hand exoskeleton, we've seen pneumatics used in a variety of different types of soft robot arms and grippers. This bottom right video shows what still represents state of the art in terms of using pneumatics for soft robot actuation. And so over these decades, there's been refinements of these architectures, but it's not really until the last about 10 years that we've seen this explosion of interest in the field of soft robotics and this almost exponential growth in the number of journal publications. A lot of this has been aided by the proliferation of new journals, conferences. So Professor Rudykh Kramer later, she'll be presenting. She's done a phenomenal job with her participation in RoboSoft, and of course there's all sorts of workshops internationally and different special issues that have also focused on the field of soft robotics. And part of the reason of this sudden interest in soft robotics over this past decade has been spurred by a variety of different initiatives. So in 2008, there was the DARPA ChemBots program, and this led to a bunch of really exciting efforts in soft robotics that go beyond just the pneumatic architectures that we saw in the earlier implementations. And so the top left is a soft robot design that uses pneumatic jamming. The bottom right is a peristaltic earthworm-inspired robot that uses shape memory alloy. Shape memory alloy is also being used in this bottom left caterpillar-inspired robot known as the GoQ bot. Other initiatives includes the RoboSoft initiative that was started by the European Commission. More recently, there's been the Chinese Natural Science Foundation Try-Co-Robot initiative. And also we recently in the US had the National Science Foundation EFRI on continuum and soft robots. Along with this resurgence in academic interest, there's also been an explosion in commercial products that incorporate soft robot technologies. And what's really exciting about this is that it represents a mix of both established robotic companies like Fanuc and Festo and iRobot, but there's also been a lot of spin-off companies, in particular university spin-offs that have been commercializing a lot of the soft robot technologies that have been discovered in university research labs. And projections suggest that there could be a very impressive growth in this field of commercial soft robotics. And so 40% year-over-year growth, which is fairly exceptional. And so very soon we'll see, even in the commercial space, soft robotics explode into a multi-billion-dollar industry. Okay, so a lot of this effort so far has focused on soft robot gripping, human motor assistance, and bio-inspired robots that for the most part are tethered. And it's only recently that we've seen greater focus on building fully untethered soft robots. And having robots untethered is very essential if we want to build mobile, soft, bio-inspired robots that are fully autonomous and that can capture all of the rich multifunctionality and mobility of their soft biological counterparts. And so, an octopus is a very popular example of inspiration for soft robots, and clearly a lot of what the octopus and other soft marine organisms can do in terms of their agility depends on having untethered functionality. And in recent years, there's been tremendous progress in creating untethered soft robots. These are just from, these pictures are from a review article in 2018, and this alone is fairly outdated. Just in the past few years, there's been even more progress in building soft untethered robots. And for the most part, they use a variety of different artificial muscle actuators. And so top left, you see the pneumatics, which is been popular in soft robotics for decades. And then you also saw examples of using shape memory alloy, as in the top right, for building soft robots. And there's also been exciting interest or advancements in biohybrid architectures. So using, say, muscle microtissue, as shown in the bottom left, to power soft robots. And so we'll see a few talks in this session that look at these biohybrid type architectures. For this presentation, I just want to focus on efforts in shape memory alloy or shape memory materials more generally. So I'll start with shape memory alloys like nickel titanium, and then at the end, I'll talk a little bit about emerging efforts in liquid crystal elastomer actuators. So shape memory alloy, I'm sure most of you are all familiar with this. The most common version of this is a nickel titanium alloy that at room temperature is fairly malleable and compliant. But when we heat it up, it exhibits a shape memory effect where it will spontaneously convert back to its original shape. And so here we've deformed it. Because it's malleable, it kind of stays in that deformed shape. And then when we heat it up, it undergoes this phase transition. And so it goes from this very compliant twinned martensite phase to this much more stiff austenite phase that restores the crystal structure back to its original shape. So this is a video I just ripped off of YouTube. Here's an early effort from my lab to build a soft robot that incorporates shape memory alloy. It's tough to see here, but there's a shape memory alloy coils connecting the joints of this crawling hexapod. And more recently, we found much more success with, instead of using coils of shape memory alloy, to use straight wires of shape memory alloy that we bend into this loop. And instead of using its shape memory effect, we're more relying on its stiffness tuning properties. And so we take our nitinol wire, we sandwich it between two layers of thermally conductive rubber. The top layer is pre-stretched so that when we bond it, the residual stresses cause the actuator to bend up. And then when we pass electrical current through that shape memory alloy, that heats it up through a Joule heating effect, and that causes it to want to go back to being straight, and that causes the actuator to kick out. That motion is fairly robust. So as you can see here, we get fairly dynamic motion and fairly significant work density output. So I'll skip this slide, but we've done extensive characterization of these shape memory alloy-based actuators to ensure that they can produce the forces and the work densities required to power soft robots. And another exciting feature of these shape memory alloy actuators is that the voltages and currents required to power these actuators can be supplied with an onboard miniaturized battery. And so this is a very promising path towards making fully untethered and eventually autonomous soft robots using entirely onboard electronics. So an onboard lithium polymer battery for the power supply, and then onboard circuitry just for the power regulation and control. So here are some early examples of fully untethered soft robots that we made using shape memory alloys. You can see on the top left, the robot is powered using a pair of lithium polymer batteries. We've printed a flex circuit board. For that matter, you could also use a rigid circuit board or soft circuit board, depending on the extent to which you want the body of the robot to be soft and compliant. But the limbs themselves are quite soft and rubbery. We have these wires, that loop of nickel titanium alloy that enables these limbs to kick out when we supply them with electrical current. So a few videos here showing locomotion in real time. And because of the high force and high work density of these actuators, we can achieve locomotion speeds that start to approach that of natural organisms, so significantly faster than previous attempts using pneumatics and other methods for actuation of these soft robots. So a lot of the effort in the past few years have focused on taking this architecture and now extending it to other modes of locomotion, and also looking at ways to create soft robot test beds to evaluate sensors, control schemes, and also simulation methods. And so a follow-up study looked at taking that same shape memory alloy architecture for the actuators and using it in the star-shaped swimming robot. Now, as you can see, the robot is fairly slow, so we have to speed it up times 10 to get it to move at a brisk enough pace. And so to improve the design, we've looked at alternatives to that original looped SMA wire. So here's kind of somewhat of a failed attempt at creating a soft robot that we were hoping would swim faster. And then finally, we converged on a design that we adapted from the Bristol robotics group. So this is a very nice implementation that uses a coil of shape memory alloy that's connected to two sides of this soft robot limb. And this also is very similar to the architecture that Barry Trimmer adopted for his Caterpillar-inspired soft robots that were part of the DARPA ChemBots project. So here, what's different compared to previous efforts using these coiled SMA wires is that we have two pairs of coils so that we can get bending not just in the plane, but also out of the plane. And that enables us to create a star-shaped robot that's able to both paddle and swim, but also move its limbs up and down so that it can crawl on the bed of a water tank. So this is our fully soft, untethered sea star inspired robot. We call it Patrick. Now, I say fully soft, really it's the limbs that are soft. I mean, we still have a rigid circuit board in the middle. Also, there's no onboard sensing. The way that we do closed loop control is using an external camera to track the motion of the star inspired robot. But still, it represents an early example of building a soft robot that can execute motion primitives and path planning using closed loop control. And in this way, it can do things like track an object. And so, here's just a static object that it's following, again, using the closed loop sensing with computer vision and that overhead camera. Here's another example showing now that target moving around. So let's see if I can get this video to run. So not perfect. There's a lot of imperfections in the design of the limbs of the soft robot, and so it doesn't quite move as effectively as we would like, but generally in terms of the gross motions, it can do the job of tracking the object. And as you can see, as the target moves, the robot corrects its course accordingly. And so this is all done with a closed loop scheme using the camera, like I said. Also, we're using the robotic operating system, ROS, for the framework for translating that feedback into commands that are then sent via Bluetooth back to the robot. And here's just another view of that same motion. We're again showing as we move the object, the robot can correct its path. So this, for us, at least for my lab, represents the state of the art of what we can do with an untethered soft robot. At the very end of this presentation, I'll talk about next steps in terms of getting onboard sensing so that the robot isn't dependent on an external camera and an external computer and controller to do all of the motion planning. For the second part of this talk, I'll talk about efforts to replace those shape memory alloy actuators with liquid crystal elastomer. And the advantage of liquid crystal elastomer is that it's much more compatible with processing techniques, so we can more easily shape the liquid crystal elastomer into desired 3D soft robot architectures. And these materials are also 3D printable. Now, the basic principle behind liquid crystal elastomers is fairly simple and quite similar to what we saw with shape memory alloy. At room temperature, the material is quite soft and malleable. So you can see when the clip replays that when we stretch it, the LCE remains stretched. And then when we heat it up, it undergoes this phase change that causes the material to return back to its original shape. And like I said, LCEs, and a nice feature of these and an advantage over shape memory alloys like nickel titanium is that they're 3D printable. And there's been a series of very nice studies that have demonstrated that in recent years. Here is a video from Jennifer Lewis's lab at Harvard that shows direct write printing of liquid crystal elastomer. Around the same time, in parallel, there was also very nice work done by Ravi Shankar at University of Pittsburgh, and also Taylor Ware then at UT Dallas, now at Texas A&M, where they've also demonstrated 3D printing of liquid crystal elastomers. And here's another clip from the work from Jennifer Lewis's group, showing that after printing, you can go and operate these LCEs just like you normally would, and you can get shape-changing properties through heat. So in this case, they're placing the LCE array on a hot plate, and that thermal activation causes that shape change, as you can see here. I'll just play that video once more. Now, a limitation with liquid crystal elastomers is that they're not intrinsically electrically conductive. So unlike nitinol and shape memory alloys, you have to apply external heat. So using a hot plate or a heat gun to induce that shape memory transition. And so obviously, using that kind of external thermal activation isn't practical for fully mobile, untethered soft robots. And so there's been interest in incorporating electronics, joule heating elements into liquid crystal elastomer so that you can, in a sense, kind of in situ, induce that phase change. And so this is a very nice study by Mike Tolley and Shenkong Kai at UC San Diego, where they've demonstrated the ability to make soft actuators in which electrical joule heaters are embedded within the LCE so that you can achieve that thermal phase change without reliance on an external heater. And this is, to best of my knowledge, a first attempt at building a fully untethered soft robot that uses liquid crystal elastomer actuation. Now notice it's sped up 80 times, but still, I think a very important early proof of concept for this overall approach to creating untethered soft robots. So how can we improve upon this? Well, something that my research group has looked at is that instead of using the serpentine metal wiring that the UCSD group use to activate these LCE actuators, we decided instead to use liquid metal. And liquid metal is another area of intense research focus right now. There's been quite a number of examples of using liquid metal alloys like eutectic gallium indium for highly stretchable circuit wiring and then also sensing. And more recently, we've also been looking at using liquid metal for embedded Joule heaters for activating materials like liquid crystal elastomer. And so here on the top right, this is this old video that I took back when I was a postdoc at Harvard working with Rob Wood, in which a microfluidic channel of liquid metal is embedded in a soft strip of silicone rubber. And so as you can see, as we stretch that strip, the circuit remains intact, so this LED stays on. And the idea is that if we take that same microfluidic channel and embed it within liquid crystal elastomer, we can use this stretchable circuit wiring now as a Joule eating element to induce that thermal shape change within the LCE. And so that's what we've done here. Now to create those microfluidic channels, we've used a UV laser micromachining system. And so we've deposited a very thin layer of liquid metal on top of the LCE and just used the UV laser to ablate away, remove the excess liquid metal, leaving behind these traces that we then coat with an additional layer of liquid crystal elastomer. And here's that actuator. It's tough to see the liquid metal traces just because they are fairly thin. We get fairly good resolution with the UV laser micromachining, but still, there's enough electrical connectivity there to pass electrical current through and induce that phase change. And what's particularly interesting about this approach to creating these electrically powered LCE actuators is that the liquid metal channels not only function as Joule heating elements, but they also double as sensing elements. So we know from Poulet's law and Ohm's law that as you take a conductive material and as you deform it, so as you change the length and you change the cross-sectional area, that leads to a change in electrical resistance. And so through that principle, we can create this self-regulating actuator that as it deforms and contracts, that resistance changes. And then we can use that change in resistance to determine whether to activate the actuator again, so to resupply it with electrical current. Another approach that we've taken to incorporating liquid metal into liquid crystal elastomer is to, instead of using microfluidic channels of liquid metal, to use droplets of liquid metal. And so we've developed ways that we can control the size and dispersion and spatial distribution of those droplets within our LCE composite. And so this is typically done using a shear mixing method where we vary mixing time, we vary the mixing speed, and we also vary the curing time. We can also process these LCE liquid metal composites so that they become electrically conductive. This is something that we had previously observed with other composites of polymers in which we suspended liquid metal droplets. And so this is based on a mechanical sintering principle that Rebecca Kramer's group had initially discovered back in 2014. So they had a really beautiful paper published in Advanced Functional Materials where they demonstrated that if you had droplets of liquid metal on a substrate and you applied really intense pressure, that you would get those droplets to rupture and form these electrically connected pathways. And so since then, we've demonstrated a similar effect when the liquid metal droplet is inside a soft rubber matrix material. So in the top video here, we're applying pressure on a composite of liquid metal droplets inside a soft silicone rubber. Another very interesting feature of these composites is that they exhibit fairly stable electrical properties even when stretched to very extreme strains. And so this is a composite in which we've, again, mechanically sintered it. So those liquid metal droplets are forming these percolating electrically conductive pathways within the rubber. And so you can see the strip is conductive, and so we use it to power this LED light. And not only does it remain conductive under very extreme strains, but the electrical resistance from one end to the other remains almost constant. And this is in almost complete violation to what you see in Poulet's law, where you would expect that as you increase the length, as you reduce the cross-sectional area, you would get this exponential rise in resistance. In contrast with these liquid metal embedded elastomer composites, we see that resistance remains stable. So for all these reasons, we think of these liquid metal droplet networks as being especially promising to make LCEs electrically conductive so that we can do direct electrical activation to induce that shape memory effect. Here's some other studies looking how we can suspend liquid metal droplets within, say, a thermoplastic elastomer SEBs to create 3D printed composites that are electrically conductive. Also, we can embed these in thermoplastics that exhibit self-healing properties. And so what this goes to show is that with our processing methods, we can suspend these liquid metal droplets and achieve these percolating electrically conductive networks in a fairly wide range of different polymers. And so that's enabled us to create these liquid metal LCE composites, where, as you can see here, with very high volume fractions of liquid metal, we can get electrical conductivity, and we can get the LCE to exhibit shape memory effects in response to direct electrical activation. Still rather slow, and so we haven't really reached speeds that are too much better than what was previously showed by the UCSD group. But still, we're making progress in creating these actuators that are a little bit more robust and more responsive to electrical input. In terms of the properties of these composites, the stress strain response and the overall mechanical stiffness of these do vary somewhat with the with volume fraction of liquid metal, but for the most part, these composites remain elastic, so they are able to maintain their nominal strain limit, and their modulus is still within that in the ballpark of about 1 megapascal. Because of the high metallic loading fraction, we see enhancements in thermal conductivity, which is particularly important for thermal activation, because we want to be able to rapidly bring heat into these materials, and we also want heat to rapidly dissipate as we allow the actuator to relax. And all that is enabled with this enhancement in thermal conductivity. And that's something that also turns out to be in fairly good agreement with theoretical predictions that we've made based on effective medium theories and formulations for how thermal conductivity should increase as you increase the metallic loading of these types of polymers. And lastly, and perhaps most importantly, even at these high volume fractions of liquid metal, we don't influence the shape memory properties of these materials too significantly. So when we do DMA studies of these composites, we find that for the most part, the storage modulus of these materials and how that storage modulus changes with temperature pretty much remains intact, regardless of the presence of liquid metal. And also the amount of contraction that we see as we change temperature also is pretty similar when we compare the unfilled and filled liquid metal composites. And then in terms of the electrical conductivity and electromechanical coupling, again, we see that when we form these electrically conductive traces within the LM-LCE composite, that as we stretch the composite, we don't see significant changes in electrical resistance. And that's significant because that tells us is that as we actuate these composites, we don't have to modulate the amount of current or voltage that we apply in order to maintain that fixed Joule heating. And so overall, the electrical properties of our composite remain stable even under these extreme mechanical deformations. So here's an example of a LM-LCE sheet where we've used photoinitiator to do UV-based programming of these composites so we can get them to form different shapes in this reversible way. Now, in this case, we are using a heat gun to activate. Here's an example where we're activating using direct electrical Joule heating. And in contrast to what you might expect, adding the liquid metal droplets instead of making these composites more brittle or more fragile actually makes them much more tough and much more resistant to tearing and mechanical failure. So we end up with fairly resilient composites where you can puncture them, tear them, they remain both mechanically and electrically intact. We can also utilize the interesting and robust mechanical responsive properties of these materials to create composites that even exhibit some degree of embodied intelligence. So here's an example of a composite where we've selectively created a conductive trace through the composite to connect this LED light. But as we damage the material and rupture the embedded liquid metal droplets, we end up creating a new electrical pathway that not only bypasses this LED, but induces an actuated response that results in this kind of this autonomous actuation of the LCE in response to that damage. So I'll just end here with a few notes and areas of improvement in future study. More generally, why untethered soft robots? Well, for one, it does represent a critical step towards building fully autonomous soft robots. These systems can also be useful testbeds and platforms for exploring questions in biologically inspired robotics and also the locomotion of natural organisms. They can also be testbeds for evaluating novel forms of sensing and control. And something that my group has been particularly interested in is using these robots as testbeds for validating various physics engines that we're developing for rapid simulation of soft robots. In terms of using shape memory materials, so shape memory alloy, we've demonstrated that you can get relatively fast walking, at least compared to other modes of soft robot actuation. And so we're able to approach about a body length per second of walking, which is comparable to natural organisms. The operational runtimes are sufficient for performing tests, but there's certainly room for improvement. So with those lithium polymer batteries, we can get about 30 minutes of runtime before we have to recharge the battery. Now, the Patrick star-shaped robot that I showed you, that used an external camera for a closed loop feedback control. And so next steps would be using onboard sensing for proprioception, motion tracking, and also obstacle detection. And we would also want onboard computing for all of the decision making and path planning. And down the road, as progress in untethered and autonomous soft robots are made, it'll increasingly important to identify important use cases where autonomous soft robots have certain advantages over other types of robotic technologies. Lastly, with liquid crystal elastomers, they can be 3D printed. They do have sufficiently high work densities to power soft robot locomotion. Their work densities are comparable to natural skeletal muscle. And they can also be engineered so that they're electrically conductive, so that they can be activated through Joule heating. So next steps for us are to work with our collaborators at Texas A&M, Taylor Ware's group, to create 3D printed LM-LCE composites and use that to create electrically responsive soft robotic systems. So that's it. I'd like to close by thanking our collaborators and also members of my research team, the Soft Machines Lab, and also like to acknowledge our sponsors. So I think that leaves us with quite a few minutes for Q&A. So happy to take any questions.
Thank you very much, Professor Majidi, for this great talk. Yeah, we are open to questions. I got one question through the Q&A session here open, and it asks a question regarding the stress, the force or stress that liquid crystal elastomers can produce. I think that you showed this on a slide, but extending this a bit to this question to a benchmarking comparison in your view of the materials that you discussed, that you showed us from the point of view of strain and stress and applicability to untethered actuation. So if you yeah,
sure. So I think for me, when I think about, oftentimes it can be an apples and oranges comparison, just because different actuators, they have different potential form factors, or you can engineer them into different dimensions and geometries. To me, the metric that I think is, at least for me, very helpful in comparing performance of different actuators is the Young's modulus of the material. That gives you roughly a ballpark sense of the types of stresses that those materials can support. So in the case of liquid crystal elastomer, its Young's modulus is about 1 megapascal. And you saw that if I go back here to the mechanical characterization, the modulus is about a megapascal, and the strain limit is about 150 to 200% strain. And what that tells us is that we can take this material, we can stretch it to say 100% strain. And so that's going to correspond to, roughly speaking, it's not quite a linear response here, but we do see this monotonic response. So at about 100% strain up to 150, 200, we're seeing roughly about 0.2 to 0.4 megapascals of stress. So that's pretty significant stress that these materials can support, fairly similar to the amount of stress that your natural muscle can support. I would say with muscle, maybe you can go a few factors higher, so maybe up to about a megapascal, but still we're talking within the same order of magnitude. However, this is way off from and way smaller than the types of stresses you can support with shape memory alloys like nickel titanium. In the austenite phase, those materials have a very high Young's modulus, more on the order of tens or even hundreds of gigapascals. Now, granted, the strains aren't quite as much, and so you'll be multiplying that Young's modulus by a much smaller number to get the effective stress that those materials can support. However, even then, we're still talking on the order of hundreds of megapascals, even gigapascals. So at least 2, possibly even 3 orders of magnitude more force that you can support with shape memory alloy versus LCE. In practice, that just simply means that whereas with shape memory alloy, you would have these very thin wires or these coils to support the types of forces you need. In the case of liquid crystal elastomer, you need just big bundles of the material or much larger volumes of that material. Again, analogous to how you would need just larger volumes of actual skeletal muscle in order to support those larger forces. And so these do, in some respects, kind of represent 2 ends of the spectrum in terms of the force and work density of materials, but you can still work around it. You can just simply compensate by just using greater volumes of liquid crystal elastomer. I will also point out that the density of LCEs are about almost an order of magnitude lower than nitinol. And so you can have much larger volumes without having significantly much more weight.
Yeah. Thank you very much. I have several more questions, and 2 questions are coming from the same person. I'm reading one by one. Could you comment on the strain and filling dependence of electrical conductivity of the liquid metal polymer composites? And the second question is, where are the percolation limits? What are the percolation limits?
Right. So excellent questions. We haven't systematically looked at that for LCE LM composites, but we have looked at it for other types of liquid polymer composites. What we found is that the percolation threshold is about 50% by volume of the liquid metal. Now, nominally, you could have composites with a lower overall volume fraction of liquid metal that are also electrically conductive, but that requires on having that liquid metal droplet settle. And so in cases where you have, as you can see on the left here, very low concentrations, if you extend the curing time, that will give time for the liquid metal droplets to settle so that locally you'll kind of hit that 50% by volume percolation threshold. But that typically is the magic number. Now, going kind of beyond that 50%, you get even more electrical conductivity. That's not something that we've systematically looked at, but it is something I would expect. If we go to kind of the farther extreme, then we start bumping into some of the work that Rebecca Kramer's group had shown previously, where they would have very high concentrations of these liquid metal droplets with no surrounding polymer matrix material. And so I guess, really the concentration was just limited by whatever air gaps you had or whatever kind of surfactant you had on the liquid metal. And in those cases, when you kind of mechanically sinter, then you pretty much get back to restore the bulk conductivity of the eutectic gallium indium. And so, yes, I mean, to answer your question, there is a percolation threshold and you would get increasing conductivity as you go to higher and higher concentrations of liquid metal.
Another question is, can liquid crystal elastomers be biocompatible to replace tissue in the human body?
Excellent question. And that's something I'm actually not too sure about. So we've started doing cytotoxicity studies and looking at biocompatibility of various liquid metal polymer composites, but we haven't yet tested with these liquid metal LCE composites. And liquid crystal elastomers more generally, I'm not aware of studies that have really kind of systematically looked at biocompatibility. I think that might still be an open question.
Thank you very much. And the last question is about shape memory alloys. Shape memory alloys are more prone to fatigue, hysteresis, etc. How can it be tackled? I believe in context of robotics as well.
Right, excellent point. So what we've observed and what we've kind of learned in our own studies, that these materials, they can withstand cycles. I mean, we've ourselves tested hundreds of thousands of loading cycles with the shape memory alloy. We haven't seen too much evidence of fatigue, and I am aware of studies that have looked at with slightly different alloy compositions where you can achieve millions of loading cycles, so very high fatigue life with shape memory alloys. In the case of liquid crystal elastomers, I believe we've gone to close to 1 million loading cycles, and we haven't seen significant fatigue with those composites. In general, I would say the LCEs are probably a little bit more promising than nickel titanium. But like I said, I mean, there has been nice progress. So kind of Dick James at University of Minnesota and the folks at in Germany have kind of looked at new types of alloys that have superior fatigue life for shape memory alloy.
Yeah. Thank you very much for taking these questions. Thank you very much for your talk. Let's move to the next speaker. I'm pleased to invite our next speaker, Professor Ingrid Graz from Johannes Kepler University in Austria, to talk on soft robotic systems inspired by plants. Please, Professor Graz.
Hello, everyone, and thank you, Aslan, for the nice introduction. It's a great pleasure to present my work here, and I'm grateful for the organizer to giving me the opportunity to talk about my work. Today, I would like to talk about soft robotics inspired by plants. And the first question I would like to ask you is, can plants move? So what you see here is a little video clip from the movie Guardians of the Galaxy. And you see the baby Groot, and it's running. So baby Groot is a plant-based extraterrestrial. And of course, plants cannot move like this. But this is another video clip from the same movie. This is baby Groot sitting in a flower pot, and it's kind of dancing. And this is closer to reality, what plants can do. So before we dive into matter of things, I would like to talk shortly about plant movements. And there is basically two types. One is called tropism. And this means you always have a movement oriented towards or away from an environmental stimulus. And you all know phototropism, which means that the sunflower basically arranges its flower towards the sun. Or there is stigmotropism, which means that tendrils of plants wrap around stems. Or chemotropism is when you basically build out seeds or fruit due to pollination. Hydrotropism is when plants move towards water. And gravitropism is basically that the plant, when you put the pot on the side, the plant will always move away from the gravitation, so upwards. And the other movement that plants can actually undergo is called nastic movements, and they are not oriented at all. So neither towards or away from the stimuli. Again, there is a multitude of environmental stimuli that can actually evoke nastic movements, such as touch, temperature, humidity, light irradiance, weight, chemical and nutritions. And so with this short excursion, we go back to the question, can plants move fast like the little baby Groot in his flower pots? And the answer is yes. So I'll show you now two plants. One on the left side, this is the Mimosa pudica. So basically you can see when it's touched, it's kind of slowly, or not really slowly, kind of fast folding its little leaves away. And on the right side, you see the Venus flytrap or Dionea, which is basically catching this bug when it's basically moving across the inside of the Venus flytrap and to eat it. So in both cases, these are tigmonastic movements. So basically it's nastic movements. They're not directed towards the source or oriented to the source of stimuli. And what you can see, this is quite fast. So you would not assume that a plant can move really, really fast. And so what's the origin of these fast movements? And there is a very nice study by Skrotheim and Mahadevan, where they basically looked how or why plants can move really fast. And so what you see is actually a plot of time scale, so time how fast a movement can be, versus the tissue size in meter. And what they basically found is there is two mechanisms that actually drive fast movements of plants. One is actually water-driven movements by swelling or growth, and also driven by the cell wall pressure. It's called Tugor. So if you look into this, you find a lot of things. This is actually how the mimosa is actually moving. It's a water-driven movement. Mimosa is here. Sorry. And the other way to really move fast for plants is actually mechanical instabilities, buckling or cracks. This is how the Venus flytrap catches the bug. And this is actually, here is the Venus flytrap. And beyond this red line, there is no movement possible. So this is, the tissue size is too big and the time is too fast to actually allow any movement. So basically you have these two distinctive approaches for plants, how they can move. One is the water-driven and one is the mechanical instability. So now we want to jump right into the mimosa and take a closer look. So the mimosa uses kind of swelling and shrinking, so water-driven movement, to actually fold its leaves. And what it basically see here, this is the stem of the mimosa and where the leaf kind of meets the stem. So here again. And what basically makes the movement is called the pulvinus hinge. It's basically a layer of cells. And in the top layer of the cells, the pressure inside the cell basically is smaller than in the bottom layer. So and if you kind of reverse this, so if the top layer basically has a higher pressure than the bottom layer, then the little leaf will bend. So basically you have an antagonistic shrinking and swelling, which takes up to 20 seconds to basically, for the mimosa to basically fold its leaf. And now we actually thought this was a very nice approach to do some swelling and some shrinking. And we tried to implement this concept for soft robotic elements. And what we came up basically is we built what we call a phase change actuator. So we built elastomer reservoir, so elastomer with a liquid reservoir in this liquid reservoir, we embedded a resistor, and then we sealed the reservoir on top with a very thin elastomer membrane. In this case, it's polydimethylsiloxane, so silicone rubber, Silgard 184. And then we supply power to our resistor, and we basically heat the low boiling point liquid that's filled in the liquid reservoir, and it starts to evaporate. The pressure increases, the volume increases, and we basically have a deflection of the membrane on top. So we achieve a volume change of about 200–300%. And so this is nice by itself. But if we now look first at the applied blocking forces, we see we use different liquids. We use acetone, ethanol, and water. And we can, with ethanol, with acetone, we can achieve blocking forces up to 6 Newton. And what's also interesting is you assume it takes a while for the ethanol to heat up and evaporate, but you would assume it takes very long time for the ethanol to cool down and basically condensate again. But this is not what we're observing. And it seems that actually the membrane that seals on top is aiding the cooling of the gas by kind of compressing it again. And so we do see we have kind of a fast actuation and also coming back to the original state. So what we then tried next to build little hinges. So we set 2 of these kind of little bubbles next to each other. So they're pushing against each other. And what you see down here is one of these little hinges. And you can see that if these little bubbles push against each other, you can actually achieve a larger movement, and you can realize a little gripper, as you can see here. So we have here always 2 hinges and 3 arms, and we can have this little gripper. Or this is a little bit more sophisticated version. It's a little 6-legged robot, and it can first bend the legs in so forward and backwards, but it also can bend them downwards and upwards. And you can see this is like real time, so it's quite slow still, and it was not optimally designed, so it's a little bit heavy on the middle part. But the idea here would be that it carries its own battery pack and would be like autonomous robot. Okay, and with this, I would like to jump now to the Venus flytrap, as I was telling you. So the other mechanism that plants use for fast movements are instabilities. And in this case, this is a so-called snap-through instability. So basically, when you look at the Venus flytrap in its open state, it's not visible in the first video, but basically you have this kind of concave shape of the Venus flytrap. And when an animal crosses the so here you can see these touch hairs. When they are crossed by an animal, the Venus flytrap undergoes a transition. So basically a snap-through instability, and it undergoes from concave to the convex shape, you can see here. This snap-through transition is very fast. Compared with the mimosa, you remember it could take up to 20 seconds. So this has a time frame of about 100 milliseconds. However, to basically reconfigure to the concave shape again, this takes hours for the Venus flytrap to basically go back to the concave shape. Okay, also we wanted to explore this concept, and what you see here is the pressure volume curve of a rubber balloon. So basically you have the pressure and the volume, and if you inflate the balloon, this is exactly what you can feel at the beginning. It takes a lot of pressure to kind of like really achieve a small change in volume. But as you reach a certain point, the volume just increases fast, whereas you don't have to apply a lot of pressure. And what you can also see, what's very interesting with this curve, it's kind of N-shaped. And you see that at a certain point of pressure, so I like take this pressure here, you have 2 states of volume that are possible. And so what we thought was now to actually try to use this kind of 2 possible states and try to see if we could jump from here to here. And actually this is possible. This is called a snap-through instability. So if you were able to come up to this point and keep the pressure constant, you would be able to jump here. but normally it's not possible. You can neither control. And so what you basically will achieve, you will jump along the hyperbola of the gas. So you basically would jump from here to this point along the hyperbola. And then if you basically reduce the pressure, you would go back on this curve and then jump back to this point. So what we thought would be interesting to see if we could sit somewhere here close to the maximum and then slightly increase the pressure and jump. And since we have explored before the low boiling point liquids, we actually came up with the idea to build a system that actually uses the vapor, so the vaporization of a liquid, just to do this little change of pressure. So what you see here, this is our experimental setup. So basically it's a beverage can made from aluminum. It's sealed on top with elastomer, and the whole thing is connected to an air supply. So basically we pre-pressure the whole system. And then here we have a low boiling point liquid. In this case is acetone or ethanol. And at the bottom we have a resistive heater, again like a resistor. So this is a 24 ohm resistor. And as we basically set our pressure point to this point and then slightly heat up the liquid with the resistor, the pressure increases and we achieve the snap-through instability. So what you see here is the photo. So basically this is the state when we start. And this is our instability when we triggered. And what you can see, I'll explain in detail, we have the instability, it takes 4 milliseconds, this snap-through instability, to jump from the small volume to the big volume. And the interesting thing is as well, we don't need too much heat or too much power to actually achieve this. So the warmth of your hand is sufficient to trigger this instability. So this is what you see here. And here is a video of the instability. So basically what you can see, I'll basically go back. So what you see here, this is how we set it. And then as we start to heat the liquid, low boiling point liquid, we have this huge volume change up to 300%. And now when we reduce or stop heating, basically we will have a snap back, but this is significantly slower as we basically follow the hysteresis curve of the rubber balloon. So if we now look here, so basically we slowly increase the pressure in our reservoir externally, then we are sitting at this point 2, and then as we slightly increase the pressure by evaporating some liquid, we basically have the snap-through instability. We jump here, and so we have an expansion by 400 to 300% in about 4 milliseconds. And then slowly it will keep on expanding. And then we basically, when we go back, we follow the hysteresis of the rubber balloon, and then we have the snapback. So what we can achieve is really like a very fast actuation. So what I show you here is a little mock-up. So we basically thought how to use this, and this is what we came up with. Sorry, it's not working. Oh yeah, now it's working. So basically, you could have some claws, and then basically use the instability to basically open the claws and have the hold state when you basically not have the activation or trigger the instability. So this would be a very, very simple way to build a hybrid robot inspired by plants. Okay, so I think I was too fast. I would like to acknowledge the students who basically did all the work and my funding buddies, and as well Professor Siegfried Bauer, who was my mentor while I worked at the soft matter physics group. And with this, I would like to thank you for your attention. And yeah, I'm happy to take any questions. Thank you.
Thank you very much, Professor Graz, for this outstanding talk. Actually, we are ready to take questions. We have this amount of time. We have 15 minutes more. So while the participants are preparing their questions, I will start with one. Mm-hmm. That's an amazing work, and I remember that I saw your work, and when I worked on phase transition composites, and that's great and that's nice. And the main thing that I was asked when I worked on phase transition, heat-induced phase transition, was, oh, but this is slow. So what is how can you see application of this nice effect? It is thermally activated, right? How can you see it, and which limitations you see, and probably how to overcome this?
So I think I'm working at the moment with some companies that are interested on impact protection. And if you assume you have something hit a surface very hard, if you achieve to really transmit the heat you generate, the dissipated energy very fast to trigger this instability. And if you see at this 4 milliseconds that we achieve, this is about the time that you would need to do some protective measures in automotive, like inflating an airbag. So if you were able to kind of translate the energy of an impact to heat, to really trigger this instability, that would be sufficient. I mean, with both of these, applications have their challenges. So with the snap through instability, you always have to really keep the pressure at a certain point, and this is a very big limitation to really adjust the pressure accordingly. So this is the limitation there. For the phase transition actuator, when we basically heat, this would be easier. And I mean, in the previous talk, and other people tried also to use SMAs or liquid metals to do this kind of phase transition. I mean, one of the big backdoors there is actually that the elastomers are not gas tight. So basically you lose material as you do the actuation. So this is one thing that needs to be tackled. But I mean, for very specific application, it could be interesting.
Yeah, especially when you can transfer heat into...
that would be one of the things that would be really interesting.
Yeah, ultimate. Thank you very much. So I have several questions in the meantime, and I'll just read. One of them is, how do plants increase pressure in the capillary?
Basically, so this works with osmosis. So basically, I should actually have prepared a slide, but basically plants transfer water with osmosis to and from the cells. So they direct this.
Built-in, what is called?
Built-in, yes.
Okay. Yeah,
what do you want to achieve?
Yeah, thank you very much. I'll move to another question. In comparison to the unstable to stable condition, as I understand in this instability effect, how much energy is needed to go from a stable condition to the unstable condition? In the
for the actuator?
Yeah, I think so.
I think so. So basically, in our case, I mean, we were able to determine. So I was by 500 watts. So give me a second. I have a slide here. So basically, here you can see with the snap through, to trigger the snap through, it's about, so what we measured, it's about 500 watts. For the duration to heat, to go from the stable to the unstable transition, to the snap through.
Okay. Okay, so thank you very much. Let's move to another question. It says, nice work. Does the hydrophobicity of the elastomer and adhesion of ethanol, acetone, etc., influence the performance?
Not that we did see any problems. I mean, what I said, what we found interesting, that it was actually the membrane was the rubbery nature of the membrane was aiding the cooling, but we did not observe any problems. I mean, yeah, not that I'm aware.
Okay, thank you very much. One question from me regarding this. The membrane is elastomeric, and there is naturally there's the diffusion and escape of
course, yeah.
Yeah. Does this influence significantly? I mean, do you feel is it noticeable, the escape?
No, I think we were quite lucky to some extent, because we had used quite small devices, so we were able to do like an actuation, and we also use it quite fast, so we were able to do like 10-20 minutes without significantly using. I mean, when you look at the actuators, we always have a refill chamber. But ideally, you would try to seal it with something like perylene that's gas tight. So still have the mechanical properties to keep on to allow for the movement, not hampering the movement, but at the same time sealing it a little bit, because on the other side it's thick enough that you don't have so much diffusion or evaporation. But on the top membrane is maybe mainly the problem. But you could see actually actuation got better because the liquid was already in a heated state, and we did not see that much loss of low boiling point liquid, so of working liquid. Surprisingly, I'm quite surprised. I was surprised myself. I thought we would lose a lot more.
Yeah, but perylene solves this.
Perylene, yeah.
Yeah. Okay, great. Thank you very much. Okay, we have several more questions here. Very interesting work regarding a snap-through using phase change. In voltage-actuated elastomers, we notice that when the voltage is reduced, the rubber balloon gets stuck in a bistable large volume state. Once the snap-through occurs in the rubber balloon, based on the phase change, how is the pressure reduced to achieve the snapback? I will repeat, once the snap-through occurs in the rubber balloon, based on the phase change, how is the pressure reduced to achieve the snapback?
Yeah, basically, so if you, sorry, give me a second. So we basically here, I mean, the setup basically has this kind of valve where we can adjust the pressure constantly. And as I said, this was one of the main problems as well, to keep the pressure really at the points below. So ideally, you would calculate or simulate an according reservoir size where you would kind of try to solve that problem. But we obviously here have the valve and the inlet for the liquid, and we adjust the pressure accordingly.
Okay.
To come back. And in this case, basically, once the liquid is completely evaporated, obviously it starts to cool again with the membrane. And this is basically where you come down this kind of pressure curve as you reduce the pressure.
Thank you very much.
And you see as well, when it's touched, it's basically heated up, but as soon as you remove the hand, it starts to cool, and then you follow the pressure volume curve downwards and jump back.
I see. Thank you very much. We have 2 more questions here. Given the very rapid motion with the Venus flytrap like mechanism and the possibility and the possibly high stress acting on the membrane, do you have any estimation on long-term stability, repeatability, such that it could be applied to for industrial applications?
Okay, so yeah, so maybe there's two important points. Of course, we do see like the Mellon's effect. So we do see a softening of the rubber. And I forgot to mention this. So in this case, we actually use natural rubber, because the natural rubber has this snap-through instability. We could not achieve the same thing with the silicone rubber. And obviously, I mean, natural rubber, we have the Mellon's effect, but we do see, I mean, we did, I think, 10 cycles, and we do see a little bit of a hysteresis, but it's not dramatically. So you see it for the first few cycles, and then basically it settles in.
Thank you very much. And the last question that I see here is, when my question is that when the trapper comes to know that it has to reopen itself, when the trapper comes to know, when the trapper understands.
I think he means the person means the Venus flytrap. So I guess it's when the bug is kind of digested, and there is hair inside of the Venus flytrap that basically reacts to the touch to introduce the snap-through instability. And I think once the bug is disappeared, it basically will unfold itself and come back to the original shape.
Thank you very much. The question of my interest, you know, you show it on one. This temperature triggered snap-through instability effect. You show it on one sample, let's call it.
Yeah.
Did you think of / tried an array of these guys?
No, that would actually be very interesting. And as I said, I think the challenge here is really to adjust the pressure, because if they're all communicating, you have to have very good pressure control.
You don't need to have them communicated if they're separate.
No, we did not. We did not. I mean, I would like to actually find someone who has very good control to prepare natural rubber, very, very thin, because I should say here, I mean, it would be nice to have some material to play with. And if we could adjust the thickness of the membrane, that would also help a lot. But now we actually took what was available, and that would be another option to play. And if you had a lot of identical membranes, then we could do an array. But an array would be definitely very interesting of these ones.
Yeah. Okay. Thank you very much for your talk and for taking these questions.
Thank you.
So much. Yeah, and we move on. We will move to our next speaker. It is my pleasure to invite Professor Victoria Webster-Wood from Carnegie Mellon University in the United States to give her talk on aquatic invertebrate muscle as a farmable bioactuator for biohybrid robots. So we continue the biohybrid topic here. Please, Professor Webster-Wood. Thank you.
Thank you, Aslan. And let me get my screen sharing here. Is it sharing the right side? Excellent. So thank you for that kind introduction and the invitation to speak with everyone today. I'd also like to thank the conference organizers for putting on this great remote conference in this electronic format. Hello, everyone. I'm Vicki Webster-Wood. I'm an assistant professor in the Department of Mechanical Engineering at Carnegie Mellon University, and I run the Biohybrid and Organic Robotics group. And my goal today is to convince at least some of you that aquatic invertebrate muscle has some interesting potential and applications as a bioactuator for biohybrid robots. And before I dive in, I of course want to acknowledge all of the wonderful undergraduate and graduate researchers in my group who are the ones actually doing the work these days. This is obviously us pre-pandemic, and now we've all transformed into these tiny little boxes, like I'm sure many of your research groups have as well. And I'd also like to give just a shout out to my collaborators and mentors over the years who have really made this work possible. There's more than could fit on one slide, but I wanted to thank them as well. So the plan for this talk is that first I'm going to provide a little bit of an introduction in the challenges in biocompatible actuation and how bioactuators can kind of address some of those challenges and needs, as well as provide some background on the types of non-mammalian sources for bioactuators that we've seen in the literature, before I then get into my own work on using molluscan muscle as a bioactuator for robots. I'd also like to encourage everyone to think about bioactuators kind of beyond just the actuator. Often when we think about bioactuators, we just think about muscle. And hopefully today I'll be showing you that we really need to think about kind of these more integrated biohybrid systems. And I'll wrap up with some remaining challenges in future directions. So let's go ahead and dive right in. The research in my group is really kind of driven by this question of how do we capture the adaptability and compliance seen in animals in biocompatible robotic actuators? And I'm really focusing here on biocompatible. As we've heard in some of the earlier talks, there's still an open question of the biocompatibility of a lot of existing soft robotic actuators. And this becomes very important when we start looking at field applications, where eventually we'd like to be able to deploy robots into potentially sensitive ecosystems. My research group is very interested in aquatic applications, such as monitoring in sensitive environments like coral reefs. And it's really important that in these environments, we're not introducing additional heavy metals or plastics that may damage the ecosystem if our robots should be lost or suffer failures. And so when we look at animals as a source of inspiration for these types of soft robots, we see that biological muscle has some very desirable properties for our actuators. Muscle has useful strain capabilities. Obviously, we are all able to get around and move. It has a reasonable power density. And of course, muscle is naturally compliant. And so we do see that there are, as you've heard about in the earlier talks so far, a number of existing synthetic actuators in the literature and commercially available that have similar capabilities and even obviously excel past muscle in many of these capabilities. And while biological muscle does not necessarily beat out all other actuators in any one category, it is good enough in kind of all of these metrics that we're looking for in actuators. And I think that we should kind of consider it as this engineering material for these robotic devices. And in addition to being kind of good enough in a lot of these categories, muscle also gives us some very interesting additional capabilities that we don't see in some of these synthetic actuator materials. For example, muscle is capable of adaptation to mechanical loading, right? We can exercise our muscle to strengthen it. Muscle is also capable of self-repair through healing, and is obviously naturally biocompatible and biodegradable. And so as a robotic actuator, I think it has a lot of potential, especially for these applications where we need something that is biodegradable. And so using bioactuators, there's been tremendous research in the last even decade looking at building soft robots with bioactuation. And this has existed across kind of a scale of sizes. At kind of the micrometer scale, we see researchers harnessing the capabilities of motile cells to drive biohybrid robots. On the scales of orders of kind of hundreds of micrometers, we see these microbots wherein researchers are able to use tissue engineering techniques to grow functional tissues and functional muscle as an actuator. And biohybrid robots is even starting to extend into more of a macro scale, where macro scale is a bit relative here when we're talking about biology. And so these are robots that are more on the centimeter size scale, where we can use either cultured cells or explanted tissue harvested from organisms to build functional biohybrid robots. And this has really been a growing field. And this slide is obviously a bit outdated at this point. And this growth has just continued. We're seeing tremendous research and public interest in the area of biohybrid robotics over the last decade. And there's been a number of different approaches proposed in the field. Many researchers are using mammalian-sourced materials, either commercially available cell lines that you can purchase and then grow the tissues, or isolating what's called primary cells from an organism such as a mouse or a rat to grow the tissues. And we've also seen approaches using invertebrate tissues, either isolating the tissue directly from the animal, or even cyborg approaches where researchers are able to harness the capabilities of things like cockroaches and flying beetles and kind of steer the organism around as a little micro robot or milli robot. And of course, as this field is growing and seeing additional interest, I think every time we talk about biohybrid robotics, it's important to kind of acknowledge the ethical considerations of the field, especially since so many researchers in this space are relying on primary cells or tissues that are isolated from animals. And so we as biohybrid roboticists really need to engage in the same type of responsible animal research that researchers in, for example, biomedical engineering follow. And this really means kind of the 3 R's of animal research. Replacement, which is the idea that wherever possible, you replace the animal need in the research with a model or a simulation, or if you can't do that, you look at, can you use a lower order organism to achieve your research objectives, right? Rather than using primates, can you use mice? Rather than using mice, can you use insects? We also want to look at reducing the number of animals we need in our research and kind of refining our experimental techniques and methods with the ultimate goal of minimizing the stress and pain experienced by the animal. And so in line with these objectives of animal research, I do want to acknowledge that for the research we're talking about today, we are working with invertebrates in that vein of kind of reducing the order of the animal. And we also fully anesthetize all animals prior to any experimental procedures and humanely euthanize the animals as part of the tissue isolation. It's also important in animal research to consider the benefits and goals of the research. And so I wanted to introduce kind of the goals in my research lab. And we have 2 kind of primary goals with this biohybrid robotics research. The first is to understand and predict the coordination and function of neuromuscular systems. And a lot of studies in kind of the neuromuscular space are conducted in animals or in isolated cells or small reduced preparations. And biohybrid robotics really gives us an interesting opportunity to expand the reduced preparations in this space so that we can design test platforms that let us study neuromuscular systems while still maintaining some sort of functional biomechanics, which is so critical to performance in the animal. Additionally, our group is really interested in creating, to the fullest extent possible, completely biodegradable robots in order to minimize the environmental impact in future applications where we're hoping to be able to deploy swarms of robots into sensitive ecosystems for monitoring. And these ethical considerations have really brought my research focus to largely focus on non-mammalian sources for bioactuators so that we can reduce the order of the animal we're working with and work with animal systems that are well studied and understood so we can reduce the number of animals that we need for our experiments. And this is, of course, not a new concept. A number of researchers have used non-mammalian sources for bioactuators. For example, researchers have used the dorsal vessel from moth larvae as a bioactuator. And other groups have used the legs of Goliath beetles for actuation, or even created cyborg jellyfish to kind of perform these aquatic monitoring tasks. And then in my research group, we focus on sea slugs, the sea slug shown here. And so that brings us to molluscid muscle as a bioactuator. And many of you are probably sitting there thinking, why sea slugs? Right. And this really comes to the long-term goals of the research, where we really want to be able to create biodegradable robots out of materials native to an environment so that when we deploy the robots in the field, they do minimal environmental damage if lost or eaten by local organisms, which is a possibility. And so sea slugs have tremendous biodiversity. Just to highlight some examples, nudibranchia exists in some form in basically every non-frozen coastline around the globe. Another type of sea slug, Opris, has a number of species with widespread biodiversity. Opris moreo exists on the vast majority of coastlines globally, with a special focus kind of here in Oceania. Opris punctata is native to many of the coastlines of Europe. And Opris californica is native to many of the coastlines surrounding the Pacific Ocean. So it is really possible to identify a sea slug native to a location where you want to deploy your robot. And in my research group, we focus on Opris californica. So these are some of the Opris in our lab. We maintain 2 saltwater reef aquariums to house the animals. And here you see kind of 3 of these sea slugs in their environment. This is right before feeding time, so they're engaged in this head waving behavior, kind of looking for seaweed in their environment. And Opris is a very robust marine sea slug. In particular for us, these animals in the US are typically from off the southern coast of California, where they live in the intertidal region. And in this environment, they live in tide pools. So they may experience large temperature and osmotic swings as the tide goes in or out or weather events occur. And to really highlight this, these animals typically live at about 16 degrees Celsius, but the tissue functions at and even slightly above 25 degrees Celsius, which is really quite remarkable. If you or I had a fever of 9 degrees Celsius, we would be in a lot of trouble. And in addition, they have very large, robust cells. So both their muscle cells and their neurons are very large. You can see individual neurons under kind of just a standard stereo microscope, which makes them an excellent model system for neurobiology research. And this means that we know a lot about the anatomy of the sea slug, about the neuromuscular system, and this helps us reduce the number of animals that we need for a given experiment. Towards kind of farming these materials for biohybrid robotics, Aplysia undergo a well-documented life cycle. And the National Resource for Aplysia at the University of Miami actually farm raises these organisms for scientific research. They start life from these egg masses and are initially a free-swimming veliger, excuse me, which undergoes metamorphosis into kind of a more adult form factor. And then they just get bigger and bigger over their lives. And so I've seen these slugs, especially wild caught, the size of kind of large guinea pigs or even small house cats, where it takes 2 people to get it out of the aquarium. And this means that you can harvest bioactuators at the desired life stage and essentially get kind of the size, the form factor, the material properties of the actuator that you need for your given robotic application. And so we're able to get them at this very small stage. This is still shortly after metamorphosis. It hasn't quite reached its full juvenile form yet. Over a course of weeks, they grow tremendously in size. And then, unfortunately, with this batch, the coronavirus lockdowns happened, and so we don't have the full life cycle of these animals. But after many months, they reach this full adult size at about 200 to 400 grams. And then from this animal, we're able to isolate explant tissue from the organism for use as a bioactuator. And so here I'm just showing we've isolated an I2 muscle from the feeding apparatus of the Aplysia. And one approach that we've taken in the past in my group is then to combine these isolated bioactuators with flexible bodies. And we can 3D print these flexible bodies using an SLA resin printer. We then affix the muscle to the robotic body, and we can pace the contraction of the muscle using external field stimulation to drive locomotion of the device. And so here you're seeing 2 electrodes in the bath, applying a pulse stimulation to the robot. Each time the pulse occurs, the muscle contracts and deflects the body of the robot. This is roughly inspired by little baby sea turtles, very abstract bioinspiration. And then each time the muscle contracts due to the anisotropy of the body and frictional anisotropy of the feet at the back here, the robot kind of scooches forward. This is real time, but obviously they do move pretty slow. Of course, these are sea slugs, so slugs are pretty slow. So this is not actually that slow for the source organism that we're studying. And in this platform, we actually see that using this external electrical stimulation, the muscle fatigues fairly rapidly. We could stimulate them for about 10 to 15 minutes, after which locomotion would essentially cease. You could let the muscle rest again and stimulate it again later, but over time, they become unresponsive to stimulation. And of course, in the actual body, in living organisms, muscle has evolved to receive stimulation from the nervous system, right? And they've kind of evolved together. And so one thing that we started thinking about is, well, should we really just be considering the muscle as the actuator, or do we need to really start thinking about kind of these integrated biohybrid systems as functional materials for actuation, where we look at how much of the biology do we actually need to get the best performance out of these bioactuators? And again, the Aplysia as a model animal really gives us a great opportunity to address this question. in particular, the feeding apparatus of this organism is very well studied. And so the feeding apparatus consists of kind of this musculature in the head of the animal called the buccal mass. We know the individual muscles that compose this structure, as well as for the given individual muscles, where the neurons are that innervate and drive these muscles. So for example, the I2 muscle shown here in red is this broad, thin muscle that wraps around the outside of the feeding apparatus, and it's controlled by motor neurons in the buccal ganglia, which are innervated by neurons in the cerebral ganglia. And with this model, we can actually isolate the muscle of interest from the feeding apparatus, in this case, the I2 muscle, in such a way that we maintain the structure of the muscle as well as the innervation to the relevant controlling ganglia. And this is really important because in biology, we know that the structure of the tissue has a really big impact on how it functions. And that's often lost in tissue engineering approaches to biohybrid robotics. And so these neuromuscular tissue circuits then let us start to look at how stimulation at different levels of this tissue impacts actuator performance. And so we did this with a number of stimulation modalities. We were characterizing the peak muscle force achievable by these actuators. And we did this just using a simple cantilever platform where the force in the muscle was calculated based on the deflection of this cantilever beam. We looked at the impact of external electrical stimulation via field stimulation, electrical stimulation via a suction electrode, where we actually suck up a little bit of the nerve that innervates the muscle and stimulate it directly, as well as stimulation by inducing natural motor patterns in the controlling ganglia. In this case, from the literature, we know that application of carbachol solution to the cerebral ganglia will induce bite-like motor patterns, which result in rhythmic contraction of this I2 muscle. And not unsurprisingly, we see that indeed stimulation via the natural neuromuscular junction improves the actuator performance. So we saw significantly higher peak muscle forces in ganglia-stimulated preparations versus either of the two electrical stimulation approaches. So with this in mind, we wanted to look at how we can use these explanted neuromuscular tissue circuits as integrated functional materials for actuation to improve the device performance. So we took our NTCs and designed a new robot body, roughly inspired by inchworms, where we have two masses for the body. The muscle is attached between these bodies, which are connected by a flexible printed spring. And then since we're only using one actuator for locomotion, we're relying on anisotropy of the feet to actually drive forward locomotion. These ganglia isolation wells allow us to place the cerebral ganglia in isolation from the rest of the tissue to apply chemical stimulants. Additionally, we developed a model of our function. Headset turned off. Functional materials for actuation. And we did this by approximating the activity in the neural circuitry using a 3-node stable heteroclinic channel and modeling the muscle as a kind of hill-type muscle model. So the stable heteroclinic channels are defined as the activity in these 3 nodes, which is dependent on neural pool time constant, the inhibition strength of the connection between nodes, the intrinsic excitation of each of the nodes, as well as sensory feedback based on the deflection of the muscle. The I2 muscle model was based on a hill-type muscle model where activation of the muscle is dependent on the activity of nodes A1 and A0, a time constant, and a max muscle activation. And then the muscle force itself is based on a strength and direction of the muscle, the minimum muscle length and maximum effective muscle length, and the length tension relationship for the muscle. And for the I2 muscle in particular, many of these parameters had been previously fit through the neuroscience literature. And we're able to use this model to predict robot performance. So we connected this with a simple model of the body. And in simulation, we can predict the activity of each of the components of our functional material. And we see that the muscle activation is this kind of rhythmic pattern. And combining that with the forces that we saw from our cantilever studies, we can predict a range of speeds that we expect the robot to move in. And so indeed, these robots are capable of locomotion without electrical stimulation. So this is the robot here. You can see the muscle here, and then the cerebral ganglia is up here. And there's no electrical stimulation in this video. Instead, we've applied carbical solution to the ganglia, and so it is rhythmically contracting and moving forward. And this is more robust than the electrical stimulation. We get pretty consistent locomotion for up to about 20 minutes, at which point all of the carbical has bound to the available receptors, and you actually have to wash it out and then replenish it, and the robot will move again. And our model of our functional materials predicted fairly well the performance of the actual robot devices. We're looking at extending this paradigm to look at functional materials with both actuation and sensing by including some of the sensory organs of the animal. And what we see with this is that if we isolate neuromuscular tissue circuits with muscle from the foot or body wall, the pleuropedal ganglia, the cerebral ganglia, and these anterior tentacles, which are chemosensitive, the chemosensitivity remains in the isolated tissue circuits. So here you're seeing on the left kind of the prep without any stimulation. And then if we apply a positive chemical cue to the anterior tentacle, in this case in the form of seaweed, we get contraction of the muscle on the same side of the preparation. And so this gives us an isolated preparation in which we can study sensory motor control, and as well as potentially apply this to building biohybrid robots in the future that are capable of tracking chemical cues in their environments. There are, however, some remaining challenges. A big one when working with biological materials is how do you predictably control your robot? Biological materials are inherently stochastic. There's a lot of noise in the system. And we actually know from the neuroscience literature that that noise is functional. It actually serves a purpose. But obviously, as roboticists, we try to avoid those types of things. So what we're doing is we're working on developing models to predictably control these tissue circuits by modeling what is known about the system and basically being able to predict a range of behaviors that we'll see in the robot. In addition, the sterile isolation and packaging of these robots is going to be critical. The vast majority of biohybrid robots that you see in the literature are in petri dishes in research labs, and there really hasn't been much in the way of field deployment. This is particularly true for these Opris robots I've been talking about today. All of this work is done, has been done so far just on the benchtop, and it's not sterile. So as soon as you isolate these robots, they're under attack by all the microorganisms in our environment. And so we only get about a day's lifetime. We're now set up to actually translate this to sterile isolations, and we'll be looking at kind of the long-term lifespan of these robots in the future. Finally, in order to really be able to farm these, right, we can farm the organisms, but to be able to farm the tissues, we need auxiliary technologies for high throughput farming and isolation. The current approach is grad student with tweezer, as shown here, and obviously that's not scalable. So moving forward, our goal is to really fully characterize and model these neuromuscular tissue circuits towards the goal of being able to control the robots. We're also looking at integrating the bioactuators with fully biodegradable bodies in order to be able to deploy these biocompatible biohybrid robots in aquatic monitoring applications. So with that, I'd like to again thank my research group for all of their hard work. We're currently funded by the NSF through 2 graduate research fellowships, as well as the C3NS NeuroNext on communication, coordination, and control in neuromechanical systems, which is supporting a lot of our muscle characterization work. And I'd be happy to take any questions.
Thank you very much, Professor Webster-Wood. It's great talk and very nice work. Yeah, we do have a couple of questions already. So the first question would be, okay, it starts really interesting work. How do you attach the muscle of the sea slug to the robot body? Isn't it tricky to get a good bond for efficient force transition? Yeah.
Yes, so that's a really great question. So the robots in the videos that you saw today, we use the very high-tech solution of using cyanoacrylate, which is essentially super glue. It's used in veterinary surgery to close wounds, and so you do get a pretty good bond with the muscle tissue. We have also looked at a couple applications where we can actually suture the muscle to the structure, and that's held up pretty robustly for this muscle tissue. We also have approaches that we're looking at where we're actually growing tissues. And in those cases, we can kind of grow and mold the tissue onto the structure. So it's more of a mechanical bond than a kind of chemical bond like with the cyanoacrylate.
Thank you. Okay, we have 2 more questions here. I think one of them you just answered. The question was how long the tissue will be usable after being harvested from the source. I believe this you said, right? It's pretty short time.
Yeah, right now, because we're not doing things under sterile conditions, we're not keeping them long term. I have in kind of previous experiments when I was working with more of a biology lab, we were able to isolate reduced preparations and essentially store them in the fridge even overnight and still use them the next day, even if they aren't sterile. But because it's biological material, if you're not having everything kind of under sterile conditions, you really can't keep it long term. The one great thing about the invertebrate muscle is that it metabolizes and respirates really slowly. So we really do think that we can keep these for quite a long period now that we have the facilities set up to do these sterile isolations.
Thank you. And another question is, are there efforts to grow biological tissue in a culture that can be molded to a required shape? I believe we're talking about tissue engineering as I have the question.
Yeah, absolutely. There has been a lot of really great work in biohybrid robotics, combining with tissue engineering approaches. In those types of approaches, typically people are using commercially available cell lines or primary cells that they've isolated from an animal. And you can cast the muscle tissue around the structure of interest, or you can fabricate like muscle rings separately that you then place on your robot. And you can even use structural materials based on the extracellular matrix proteins to grow the muscles directly on a robotic device. And so, yeah, that's absolutely going on. And there's been some really promising work in that direction too, especially for potentially medical applications.
Thank you very much. One question from me. The trigger, right? We're talking about triggers. The nature knows to do it very well in our bodies and bodies of animals. And it's a pretty complex process, right? Of triggering the muscle, the contraction itself. If you zoom in, it's in our muscles. It's an incredibly complex and amazing process. What, in your view, would be the ideal triggering in robotics at this stage now, and probably in 10 years from now? When I'm talking about biohybrid robotics, of course, and
yeah.
And I'm talking about, sorry for, I just want to focus it. I'm talking about types of different types of triggering, if it's electrical or it's a chemical or any type of stimuli that can, sorry.
Yeah, no, I think that's a great question. And there are a lot of emerging technologies for triggering muscle contraction right now. Historically in the field, we saw a lot of external electrical stimulation, and that was kind of the status quo. And then more recently, as we've seen with my own work, it does look like it's really important to use some of these natural motor pathways. And so there are some emerging research efforts to kind of grow clusters of neurons, to grow a neuromuscular junction, or as I showed today, to use intact neuromuscular junctions to trigger the muscle contraction. And that definitely shows higher peak muscle forces and less fatigue. There are also some interesting efforts to use light-based stimulation through genetically modifying the cells. And basically you can genetically modify the tissue so that when you shine a light on it, you trigger a muscle contraction. And I think the kind of thinking to the future, what's going to be the best approach in 10 years is really going to depend on the applications, right? And on the development of kind of the supporting technologies, right? If there are really high fidelity micro LED arrays for this optical stimulation that you can package into a tether-free biohybrid robot, then the optical stimulation is this avenue that is really interesting. For these types of robots where we're looking at these kind of integrated biohybrid systems, we can actually use kind of these natural patterns and natural structures to stimulate the robot. So you can essentially kind of trigger sensory cues to the animal to mimic sensory cues that you know how, or to the robot, sorry, that you know how the animal would respond to. And in that way, kind of, it's almost hijack the existing structure to get the biohybrid robot to do the task that you're looking for. I think those are going to give us the best performance out of our actuator, as opposed to just using kind of electrodes. And we see the same thing in functional electrical stimulation for paraplegics, right? Direct muscle belly stimulation results in much higher fatigue than nerve cuff stimulation.
Yeah. Thank you very much for taking this questions. Let me see. I have another question here. Can you program the direction and isotropy of actuation to create complex combination of motion?
That's the goal. So we haven't done it yet with the invertebrate muscle here, because we've just been looking at kind of these one actuator systems. But obviously in real organisms, we essentially are a system of distributed actuators. And so the goal is really to start looking at kind of these more complex muscle architectures that has a slight further complication over just trying to do distributed actuation with synthetic actuators, in that the muscle is mechanosensitive. And so if you have lots of actuators interacting with each other, they're all applying mechanical load to each other, and that's going to change the performance of your actuator. And so that's something that we really need to study and see how that affects each of these biohybrid actuators, so that we can start predictably designing more complex robot structures.
Thank you very much. In the meantime, we got another question. In light of the application for use on coral reefs, will the robot eventually be strong enough to counter waves and currents?
So we absolutely have a ways to go before we can deploy these in the field. Certainly these little robots I showed today are just kind of preliminary proof of concepts. And so our goal is really to work this up to a point where they can do that. And we do have our aquariums in the lab set up so that we do have wave generators, and we can start testing that in the future. There's a lot of different strategies to deal with tidal forces and waves that aquatic animals use. Some animals are just strong enough to swim and overcome these forces. Some animals use kind of hold techniques like the sea slug to actually hold on to the surface when these waves are happening, so that they're not tossed around. And for some applications, maybe we leverage the waves and we use the waves to get us to where we want to go faster, since we see that these robots are pretty slow.
Okay, thank you very much. Thank you very much for the talk, your research, and taking these questions. Now we will have a very short break. Okay, so we are back again. Thank you very much for staying here and participating in our soft and biohybrid actuation session of IeCAT 2020. And I'm pleased to invite our next speaker, Dr. Dorina Opris from Empa, Swiss Federal Laboratories for Material Science and Technology, to talk about functional elastomers responsive to electrical and mechanical stress. Please, Dr. Opris.
Hello, everybody. Thank you very much to the organizer for the kind invitation and for giving me the opportunity to present our results to you. So I'm going to present two different topics: functional dielectric elastomer that respond to an electric stimulus, they generate force and motion, and also functional elastomer that respond to an electrical stress when pressed and stretched, and they generate a response to this stress, an electric current. Let me first start with some fundamental effects. Imagine a capacitor whose dielectric is a polar polymer with randomly dispersed dipoles. If this capacitor is charged and the polymer is below the glass transition temperature, not many changes is occurring in the material, because the elastic modulus of the polymer is very high and the dipoles are frozen. They are not able to orient in the electric field and the material is not going to deform. However, if you heat this material above the glass transition temperature, several important changes occur in the material. The elastic modulus changes several order of magnitudes, and the dipoles are able to move. Now, if you expose this capacitor to an electric field, the dipoles will orient in the electric field and the material may deform. If the material is properly cross-linked, if you discharge the capacitor, the material recovers the initial shape and the dipoles randomize again. If you, however, do not switch the electric field, but rather keep the electric field on and cool the material below the glass transition temperature, you are able to freeze in the polarization. So we are obtaining frozen in dipoles. We use these two concepts to prepare dielectric elastomers and electret elastomers. So what do we do in our group? We do molecular design and synthesis. We do device fabrication and testing. So let me start with the first topic. Dielectric elastomer actuator consists of a thin elastic film sandwiched between two compliant electrodes. When charged, then you place positive charges on one electrode and negative charges on the other electrode. And because of the interaction between the charges, and because the elastomer is incompressible, then you have a movement. And so you convert electrical energy directly into mechanical work. There are many applications for this technology. However, the driving voltage in this actuator is too high. And with this formula gives the actuation strain in the thickness is proportional with the elastic module, inverse proportional with the elastic modulus, proportional with the dielectric permittivity, and inverse proportional with the square of the thickness. So in order to reduce the driving voltage U, what one has to do is to increase the dielectric permittivity of the elastomer, decrease the elastic modulus, and decrease the thickness of the dielectric film. As you will see later, only by optimizing all these three parameters, it is possible to access actuators which are operated at low voltages. So what can one do? So if one reduces the elastic modulus, you will get actuators which are not very powerful. To reduce the thickness of the dielectric film below 20 micrometer is also quite challenging. And also the best approach would be to increase the dielectric permittivity of the elastomers. So in principle, as dielectric, you could use any elastomers. The problem is that elastomers have a low dielectric permittivity, which typically is below 3. So in order to increase the dielectric permittivity, there are several approaches one can follow. Either you take an elastomer and you blend it with highly polarizable fillers, and then of course, in order to, you can put ceramic particles. However, or you can modify the polymer with polar groups. However, the chemical modification with polar groups has the downside that the glass transition temperature is increasing because of the dipolar interaction. In order to overcome this problem, we start with polysiloxane. Polysiloxane is one of the most flexible polymer backbone. And the idea was that in spite of the fact that we chemically modify with polar groups and the glass transition temperature is increasing because of the dipolar interactions, nevertheless, we may be able to access materials which have a low glass transition temperature. And then if the glass transition temperature is significantly below room temperature, then we are able to achieve elastomers with increased dielectric permittivity. So what we would like to do is to investigate how the amount and type of polar groups affects the glass transition temperature, the permittivity, the conductivity, elastic properties, and electromechanical properties. To access such polar polymers, there are several ways. So one is to start with polar monomers like the one shown here, and to do ring opening polymerization. And we achieve polar silicons which have these N groups. The second approach is to start with a pre-polymer. And then you can see we have here the green parts, which are side groups, which are we can use for post-polymerization modification with different polar groups. in order to be able to enter in application, the starting materials has to be accessible and cheap. The synthesis has to be efficient, reliable, and upscalable, and functional N groups allows on-demand cross-linking in air. Using this strategy, we prepare a library of polymer for which we could fine-tune the dipole content and different dipoles. The first thing we look at is how the glass transition temperature is influenced by the content and the type of polar groups. So you can see here the glass transition temperature and the content of different polar groups. You can see a linear increase in the glass transition temperature with increasing the polarity. And for some polar groups, you have a stiffer increase in the glass transition temperature. What is important to note is that some of the polymers have a glass transition temperature which is approaching room temperature. So for example, this polymer which has this cyclic sulfone group. So, and this is very important because if the glass transition temperature reaches room temperature, then you lose elasticity. And also this affects the dielectric properties of the polymer. What you can see on the right-hand side is the dielectric permittivity function of molar group. You can see the expected increase in the permittivity with increasing the polarity, and different groups have a different increase in the polarity. Stronger polar groups give a stronger increase in the polarity. And now for the polymer that has the TG, which is very close to room temperature, you see that there is a drop in the dielectric permittivity. All these properties were measured on highly viscous liquids, so they are not elastomers, they do not have good mechanical properties. In order to achieve elastomers, you have to cross-link these materials. We design, and I will focus in the next slides on these two different polar groups. We designed our polymer with hydroxyl N groups, which we wanted to use for cross-linking. Unfortunately, the cross-linking reaction didn't work as expected, and this is why we have to find a different way to achieve such materials. So the idea I had is to use an in situ process in which we functionalize the polymer with the polar group and cross-link it simultaneously in thin films. So what we did is to take the polymer here. The polar group is introduced by a Tyrrell reaction, which is very efficient, and then cross-linking with this defunctional thiol. And we use this process, which is shown below. Using this strategy, we were able to prepare different materials with different content of polar groups. And the first thing we look at is how the dielectric permittivity is influenced by the content of nitrile groups. You can see a linear increase in the permittivity with the concentration of the nitrile group. The second thing we'd look at was how the mechanical properties are affected by the nitrile group content. And you can see that the material withstand more than 200% strain, and with increasing the content of nitrile group, you have a stiffening of the material and an increase in the strain at break. We also look how the breakdown field is affected by the polarity. Unfortunately, with increasing the polarity, one can see a drop in the dielectric breakdown field. We also measure the actuators. So how do we do this? We have two rigid frames on which we put a transparent membrane, which you can see over here. And in the middle, there is a dot. That's the electrode on one side and on the other side of the transparent electrodes. And when we apply a voltage on these two stripes, then you have an elongation of this black dot. And that's what we measure. That's the lateral actuation strain. And this is what is plotted here, lateral actuation strain function of the electric field. You can see that with increasing the polarity, we have a reduction of the electric field, which is needed for the actuation. And for a material which is fully functionalized with polar group, which has a permittivity of about 18 at 12 volt per micrometer, we have about 20% lateral actuation strain. This was nice, however, because of the process which we used, the thickness of the film was around 100 micrometer. And because of this, we still didn't access actuators which are operated at low voltages. This was a task which Yao and Shema achieved. So what he did is to start again with this polysiloxane, which has at every repeat unit a vinyl group, and then we'd functionalize it with this thiol via a thiolene reaction. And what he did is to leave some unreacted vinyl groups here. These were subsequently used for cross-linking in thin films. For cross-linking, we use these two different thiols, crosslinker 2, bifunctional thiol or tetrafunctional thiol. So the red one will give us a soft material, the blue one will give us a stiff material. At the beginning, our materials ruptured on the surface. I think after you have done such a hard work to do the synthesis and you see that the elastic properties are good, but the material is a catastrophe, you are a bit frustrated. But we learned actually how to prepare perfect films and also how to manipulate them. And we were able to manipulate films of a thickness of 20 micrometer, and we could also build actuators with such materials. So how do they behave? So the red one is the soft material, the blue one is the stiff material. Both have a permittivity of 18, and I compare with Elastosil. This is a commercial elastomer. It has a permittivity of 3. So what you can see here is actually that the Elastosil that requires a lot of electric field in order to actuate, and our materials, because they have an increased dielectric proper permittivity, and because they are softer, they actuate at lower voltage. In this movie, you can see the soft material. It has a thickness of 35 micrometer, and at 300 volt, it gives a lateral actuation strain of 7%. On the right-hand side, what you can see is the graphical representation of the movement, which you can see in this video. So it's at 300 volt per 300 volt, we have an actuation strain of about 7%. And you can see that the actuation is quite reversible. With the second crosslinker, we obtain a stiffer material. What you can see in the movie on the left-hand side is an actuator which is 38 micrometer thick. It actuates at 900 volt, which represents 23.7 volt per micrometer, and you see huge out-of-plane deformation. So here is the voltage, and here is the lateral actuation strain, which cannot be precisely measured. On the right-hand side, there is a material which is slightly softer. Just by tuning the amount of thiol which we use, we can tune the mechanical properties. And again, a film with a 53 micrometer thickness actuates at 900 volt, and this is because the mechanical properties, this material is a bit softer as compared to the one on the left-hand side. This material can be actuated also at high frequency. This actuator is, I think, operated at 5 Hertz and gives quite fast and reversible actuation. And this is because the elastic properties are really good. Now, this is all what I wanted to tell you about the nitrile functionalized silicon. In the next slide, I will present what about the nitroaniline functionalized silicons. To achieve such materials, we started with this polar monomer, and what we did is either to polymerize or to copolymerize with this unpolar monomer over here. So first we prepared the polymers and copolymers. They have hydroxy N groups, which we use subsequently for cross-linking into thin films. I will refer to these materials as material A. The second approach was to polymerize this material in presence of tetramethylammonium hydroxide, and then to leave the N group still active. So after we prepare the pre-polymer, then we mix it with this bifunctional monomer that functions as crosslinker. We process the material in thin films and cross-linking by heating to elevated temperature. By tuning the amount of bifunctional monomer, we tune the mechanical properties of the materials. I will refer to these materials as P. So what you can see here is the dielectric properties function of the frequency for material A. Because we tune the amount of nitroaniline in the material, you see here an increase in the dielectric permittivity with the content of polar groups. What is also important to note is the conductivity is quite low for this material. This is very good because you will expose later the material to an electric field. For the second class of material B, you can see that the permittivity is not changing very much with the frequency from 20 to almost 10 kilohertz. However, at higher frequency, there is a drop in the permittivity. And this is why, because the nitroaniline dipoles cannot follow an electric field at that frequency. The mechanical properties of the elastomers which we prepare are quite good. They can withstand, some of them, more than 300% strain, as you can see in this video. Now, how do this material behave in an electric field? The material A, for which we tune the content of nitroaniline and we tune the dielectric properties. So the permittivity for one is 18, for one is 14 and 10. You can see that actually with increasing the polarity, we increase the actuation strain at the same electric field. For the materials B, for which we fine-tune the mechanical properties, you can see that the materials which are stiffer require more electric field in order to move. And one of the best material we prepared with this nitroaniline modification was material B2. It has an elastic modulus of 250 kilopascal, and it actuates at 900 volt, as you can see here. At different frequencies, so you see the lateral actuation strain of about 7%. And the actuation is really reversible. So what do we want to do with our material? Because until now, we only make single layer actuators. What we would like to do is to use them in stack actuators. Such stack actuators are produced by Empa spin-off city systems. They use a fully automated process in which they are able to prepare such stack actuators, which are operated at 500 volts and give 5% strain. And they are highly reliable. They can be operated more than 50 million cycles at 2.5 hertz. And they are quite powerful. As you can see here, this actuator lifts 1 kilogram, and the actuator here on the right-hand side lifts 4.5 kilograms, that you can see over here. So this is very nice. However, where are we? The challenge which we are still facing is that we need a solvent-free formulation that can be printed and cross-linked into thin films with good mechanical properties. So using a layer-by-layer technique, we are able to prepare such stack devices. Let's show this one. And then after we test them, we cut them. The one which didn't function properly, we threw them away, and then we pile them. And I cannot tell you how this functions because we are still investigating them. On the bottom, you can see a material which actuates at 300 volts, which is 10 volt per micrometer. So let me now switch a bit the topic and come to electret elastomers. Electrets are known for more than 100 years. They are prepared via so-called polling process in which a wax is heated above the glass transition temperature and poured in a strong electric field while cooling down below the transition temperature. However, such electret elastomers are brittle and stiff, and if you press them, they cannot generate electricity. So the piezoelectric response is very small. Imagine there was a material that can be pressed and stretched, and that response to this stress generate electricity. Such material could be used as self-sensor or to harvest energy. Let me now introduce you a new concept which was introduced by my group. So what we thought about is to prepare nanoparticles of high glass transition temperature polymers, polar polymers, and then to embed these nanoparticles into a PDMS matrix, polydimethylsiloxane matrix, which is chemically cross-linked. Then we would like to heat this material above the glass transition temperature. There the dipoles in the red dot are mobile. If you now expose this material to an electric field, the dipoles are starting to orient. And now, if you cool the material while the electric field is still on, cool below the glass transition temperature, you may be able to freeze in the polarization. So the The blue dots are polymethyl methacrylate disperse red copolymer. This is a polymer which has been used very intensively in nonlinear optics. And because this project was new for me, I thought I can use the results from this field to interpret the results which we are gaining. So we changed it polymer in nanoparticles by nanoprecipitation. We blend it in silicon, and then we achieve materials which are highly elastic. They are not piezoelectric now. You have to pole them at elevated temperature and then in a strong electric field. We did that. And using impedance spectroscopy and thermally stimulated depolarization current measurement, we have shown that such material can be poled. And using Berliner core method, we can show that the material which we poled are piezoelectric. So what you can see in this graph is the charge which is generated when the material is stressed at about 10 Hertz, and we apply a pre-force of 80 nanometer. So you can see that the amount of charge generated is quite reversible over 20,000 load cycles. So it's quite reversible. Now, what happens if you stretch the material? So if you stretch by 50%, then you have the amount of charge which is generated doesn't seem to be influenced by the frequency. And also you can see that we can stretch the material for many times, so over 5 hours, and the amount of current which is harvested doesn't change, remain constant. So the materials which we develop are quite stable. Applications which we can see is in pressure sensor and energy harvesting. Now let me come to the end of my presentation. So what transducers did we achieve? We have dielectric elastomers with a permittivity of about 18, which are highly elastic, processable in thin films, have a 7% lateral actuation strain at 8.5 volt per micrometer. If you want now to use these devices in implants, then we will have to reduce the driving voltage to 25 volt. This would be possible with a film with a thickness of 5 micrometer. And what you can see here is an actuator. We apply a step of 100 volt, which you can see here. And here you can see the lateral actuation strain, and you can also follow this dot. So you can see that at 1000 volt per micrometer, which was the maximum voltage which we apply here, we have huge actuation. We have piezoelectric elastomers with a piezoelectric constant, which is very similar to the one of polyvinylidene difluoride, which is a very well-known piezoelectric elastomers. This material can be used as stress sensor. What you can see here is the material which we developed and which is stressed at a certain frequency. And here you can see the electrical response. It's quite weak because the contrast is not so good. I haven't talked about electropolarized dielectric elastomers. These are materials which can generate also an electric signals, and they can be used as stretch sensor or for harvesting energy. With this, I would like to thank to my co-workers and also to all people who support my work and to all this funding agency. And also thank you for your kind attention.
Thank you very much, Dr. Opris. Thanks for this great talk. It's actually great to see the material synthesis from molecular level. We just had a couple of presentations back. We had a presentation of Professor Graz, who said, we would love to have a material. It is not, she did not mean this exact material, the exact type of material that you showed in this lecture, but she said, we would love to play with materials. And we, at the beginning, we used what we've had, and this is exactly what you're doing is exactly allows to play with the material and get great properties like this incredible number of 18 that you get compared to the permittivity. I mean, compared to 3 for off-the-shelf materials you can buy. First of all, I'm inviting questions. I'm waiting for questions now. And in the meantime, while you'll prepare their questions, I have one a probably conceptual question. We are, although you reduced the permittivity and of course the voltage, which has been the main probably concerned about using the electric elastomers, the electric elastomer actuators. Which problems or issues do you see now right now and for the next probably 5 years for stacking? Because as I understand, stacking is a great opportunity for the electric elastomer actuators to become a robust actuator that does a lot of things and can do a lot of things that other actuators can do. What are the main issues? And I'm even not talking about the solvent, even beyond this.
It's a great challenge, for example, to scale up the entire synthesis. So now we have to have quite some material in our hands. You cannot play with milligrams. We have to prepare at least 10 grams to have all the characterization which we need. Dielectric, mechanical, electromechanical. However, if you now want to go into the stack actuator, you will need access to more material, and you will need to have access to a lot of facilities in order to be able to manufacture, test, and characterize all these devices. There I see the challenge.
So if we talk about industrialization of this, then probably it will be an easier case, because you will have everything, more of everything. You will have more working force. You will have more availability of more material and space to prepare more material, and probably more higher volumes of raw materials available. And application at the end, right? You're not doing a lab specimen, you're doing something there. So in your eyes, is it ready for industrialization, or at least to move to another technical readiness level?
So already polydimethylsiloxane elastomer is intensively used by the company City Systems, the spin-off from Empa, in industrial process, fully automized. And now they are scaling up the entire process. So this means that the technology is there. Only what is missing is the material. And what we don't know at the moment, we test all our material in single devices, which function quite well. The actuation is quite reversible at room temperature. However, the question is, how will this material behave if you heat them up to 80 degrees or cool them down to 30 degrees? That's something what is needed for an industrial application in automotive industry. So we don't know. And also, how will our material behave when you put it in a stack devices? We only test them in single membrane actuators. This is a step we have to overcome in the next years.
So in this case, you need to test it as a single layer and as a stacked.
You'll have to do both.
But this sounds as a lab scale experiment, or do I miss any complexities in temperature-wise multi-cyclic actuation test, or temperature dependent actuation test, or material behavior or mechanical properties testing? Is it a lab? Is it just more research that needs to be done right now, or are there special additional issues that you can see?
There is more research to be done. Yeah, we'll have to work much more.
In the meantime, I got another question from the audience. How about the thickness strain actuation? Have you measured? Is it relevant? If the thickness is too low, the breakdown may occur. So as I understand from this question, the question is concerned about the electric breakdown that can occur at lower thickness versus the properties. So can you comment on this?
What matters is the voltage. The thickness is not so important. So if you have thinner films, then you will need less voltage to apply in order to have the movement. And actually what we observe is that thinner films will withstand higher electric field than thicker films. Okay. But if you reduce the thickness, then the properties of the electrodes plays also a very crucial role. So one has to also have a look. I only presented today the mechanical properties of the dielectric. However, there is also the elastic electrodes which you have to use, and I have not presented anything about this. This is also a very important point.
Thank you very much. I have another question here. As a future application, could this be a knee harness for runners, for example, where the material could be adjusted based on areas of weakness in the knee? If this can be a knee harness for runners, where the material can be adjusted based on the areas of weakness in the knee. General as application, can you envision this?
I think it can be used in principle. You can use many of these stack actuators to support the movement. So I see, you probably saw in the movie that an actuator which weighs about 8 kilograms can actually lift 4.5 kilos. So imagine you replace this actuator, which is now polydimethylsiloxane with a permittivity of 3 by an elastomer which has a permittivity of 18. With if you do that, then the pressure, the force generated by the actuator is 6 times higher. If I'm able to increase even more the dielectric permittivity, then I can make even stronger actuators. So I think there is a potential.
Okay, thank you very much. Thank you very much for your talk, your research, and taking these questions. We will move to our next presentation. I am delighted to invite our next speaker, Professor Kramer-Bottiglio from Yale University in the United States, to give a talk titled From Particles to Parts, Building Artificial Life from Multifunctional Materials. Please, Professor Kramer-Bottiglio.
Thank you, Aslan, for the introduction and for inviting me to speak today. I'm very excited to share my group's work on reconfigurable and adaptable soft robots made from multifunctional materials. But first, to motivate this work, I want to start with the robot cliche. So when people ask you to conjure up an image of a robot, or when you ask people to conjure up an image of a robot, they probably think of something like this. So these are rigid machines that perform a repeated task. They're incredibly good at what they're designed to do. They're fast and strong and precise, but what they are not is safe for human-robot interaction, and they're not adaptable. So you don't see these robots adapting to changing tasks or environments. But when we imagine robots for the future, I think we all imagine something more like this, like animals, like ourselves. We are incredibly adaptable. We readily adapt our body configuration and behavior to changing tasks and environments. And we even adapt our body properties. For example, we adapt our body stiffness to perform both gentle and forceful tasks. So how do we do this? And how do we make robots do it? Well, I noticed something while watching all of these videos. All of these animals look at least partially soft. So let's take a deeper dive into that observation. So here's a plot of all the known animals in the world, just over 1 million at the time of this data. And as it turns out, all known animals in the world are at least partially soft. There are no known animals that are completely rigid, which is in contrast to the way that we typically design robots. And further, more than half of all known animals are completely soft. So of course, there's some asterisks on this. Completely soft animals need to be supported by their environment. For example, jellyfish live in the water or worms live in the ground. We are a fairly large animal that lives on the ground, and we require some skeletal structure to keep us standing up. Even so, we as humans are only 15% bone and 85% soft and fluid materials. So it's possible that soft material composition plays a role in our ability to interact with and adapt to our environment. And so maybe soft robotic technologies can be part of this adaptability solution, or part of the solution to the adaptability problem. So I'm by no means the first or the only person to make these observations. This is the inspiration, or part of the inspiration for this session. And I'm really enjoying all of these talks today. So soft robotics is a rapidly growing field, and there's many potential benefits to soft robots. So here's just a few soft robots that I believe showcase these benefits very well. The first is a locomotion robot that demonstrates the resilience of soft robots and their robustness to impact. This robot locomotes out to the street, and you saw it get run over by a car, and it's able to continue locomotion despite the impact. In the middle, you see an image of a soft pneumatic gripper, which is able to grasp diverse and delicate objects due to the soft material conforming around those objects. And on the right, you can see a wearable robot, which can be used to increase efficiency of the wearer's motions or augment load capacity without restricting the natural mechanics of the motion of the wearer. However, all of these robots are task specific and therefore would not lend well to any other task outside of their intended use. For example, the locomotion robot would not perform well as a gripper or a wearable robot or vice versa. So my question is this: is there a more flexible design approach to soft robots? Can we develop hardware platforms that adapt to their body morphology, properties, and behavior the way we do? So this question is really central to my group's research. At the highest level, we're working at the intersection of materials manufacturing and robotics to develop intelligent materials for robots that will allow them to adapt their morphology and behavioral control policies to changing tasks and environments. So here you can see a number of functional particles and composites that we're working on, including liquid metal particles for stretchable electronics, low melting point alloy particles for variable stiffness materials, a Pickering emulsion for printable sensors, and a fiber reinforced composite for variable trajectory actuation. And we're currently using these materials in 3 platforms that I'm going to talk about today: robotic skins, robotic fabrics, and morphing limbs for amphibious actuation. So I'm going to begin with robotic skins. Let me first define robotic skins. Robotic skins are soft, planar, elastic membranes with embedded actuation and sensing, which can impart controlled motion onto the objects that they're wrapped around. So in this way, we can turn any deformable object into a robot by wrapping it in robotic skins and controlling it from its surface. So there are 2 ways to potentially implement the robotic skin concept. We can wrap a robotic skin around an object to perform a task, and then remove the skin and wrap it around a different object to perform a different task. Or we can reorient the robotic skin on the surface of the same object. For example, in the schematic, you can see a robotic skin made from a substrate, actuators, and sensors, which is wrapped around a soft balloon. This robotic skin contains linear contracting actuators, which, when wrapped around the balloon circumference, compress the balloon. And you can imagine something like this being used for peristaltic locomotion. We can then take that same robotic skin, remove it, and reorient it 90 degrees and reattach it with the actuators along the length of the balloon. And now when the actuators contract, the balloon bends. And you can imagine something like this being used for inchworm locomotion. So you can see how controlling soft objects from their surface using attachable and removable robotic skins can generate different motions and different forms of locomotion. So now I'm going to describe the hardware in the robotic skins, starting with the sensors. We aren't able to use commercial off-the-shelf sensors due to the high strains inherent to soft systems, so we design and synthesize our sensors in-house. So our robotic skins use elastic capacitive sensors with a conductive composite for the electrodes. The conductive composite is an exfoliated graphite, sonicated in solvent, and then mixed into elastomer. So in this video, you can see the graphite exfoliation process. We basically take a chunk of graphite, soak it in solvent, and then put it in a really hot environment, in this case, a hot crucible. The solvent between the graphite flakes boils and vaporizes and pushes the graphite flakes away from each other, generating the small graphite particles you can see here. So these are by no means graphene, but they are small enough flakes that we can mix them into precure elastomer and create the conductive composite. And we use a 5-layer capacitive layup for the sensors, which reduces noise in the sensor compared to a 3-layer capacitor. So let's take a look at how these sensors perform. So we see a nice linear response to strain, electrical response to strain. We see a standard nonlinear mechanical response to strain. We can see that the sensors are operational up to about 400% strain. And finally, in this lower right plot, you can see that the sensors display high cyclic stability. So they have negligible signal drift over 100,000 cycles. And the gauge factor is also stable within moderate temperature changes. So with confidence in our sensors, we can now combine these with substrates and actuators to realize the robotic skin concept. And here are a couple of robotic skin instantiations. So I want to note that robotic skins are defined as a substrate with embedded actuation and sensing, but not necessarily tied to a particular substrate, actuator, or sensor choice or any specific layout of those components. So here we built a couple of different robotic skin prototypes with different components and different layouts. In the top row, you can see a robotic skin with parallel components. This skin is made from an elastomer substrate embedded with McKibben pneumatic actuators and our capacitive strain sensors. So the capacitive strain sensors are right behind these pink McKibbens that you can see. The parallel component layout is lendable to single curvature bodies, such as cylinders or tubes of foam, as shown here. And we wrap the robotic skin around a soft foam tube to achieve both compression and bending. And we also show multiple robotic skins added together around a long foam tube to show a multi-segment continuum robot. In the bottom row, you can see a different robotic skin made from a fabric substrate with shape memory alloy coiled wire actuators and the capacitive sensors printed directly into the fabric. The triangulation of components is lendable to compound curvature bodies. So here you can see the robotic skins wrapped around a 6-bar tensegrity structure to create punctuated rolling with a locomotion robot. So to address closed loop control with the sensors, here you can see 2 cases demonstrating closed loop control with differently actuated skins. So both cases show rectangular skins with parallel components wrapped around soft foam cylinders, and each was commanded to increase its bend angle from the upright position. Each step point starts at upright, and the steps represent increasing bending of the cylinder. So on the left, the skin was actuated with pneumatic McKibben actuators, and we used the sensor coupled to the actuator, so it was contracting on the inside of the bend. On the right, the skin was actuated with SMA coil actuators reflected in the time scale of actuation. And we used the sensor on the opposite side of the cylinder, so it was extending on the outside of the bend. In both cases, you can see that we were able to track the set point and using the feedback from our sensors. Okay, so let's look at some robotic skin prototypes in action. So here we have 3 robotic skins, the rectangular robotic skins with parallel components, and they're wrapped around this long foam tube to get this thing to kind of dance a little bit. And if you look this up online, there's music set to it. And then we can take these skins off. You can see that they're very flexible and stretchable, and we can put them on 3 different objects. So here we take those exact 3 robotic skins and we wrap them around 3 smaller tubes of foam to get 3 different locomotion robots. So the top robot has weighted end caps, and it's using a kind of grab and pull style locomotion. The middle one is not actually attached to any host body, it's just independently inchworming. And the bottom robot is attached to this foam, let me see if I can go back a little bit, is attached to this foam tube. And it has laser cut bias feet that are wrapped on so that it will move in the right direction. So the robots are intentionally hacky, since the point is to show that robotic skins can be easily combined with readily available materials to quickly create robots on the fly. So here we can use the 3-segment arm that you previously saw and now attach a gripper to make it a manipulator. So we made 2 types of grippers. The first that you just saw is 2 parallel plates with a robotic skin between them, and it just pinches together to grab that golf ball and move it to a desired location. And then we can remove the gripper and replace it with another type. Here, this is a gripper with a passive finger and an active finger performing the same task. And we can also add additional hardware to the system. So here you can see an inchworm locomotion robot with a robotic skin wrapped around a tube of foam. In this case, we attach a light sensor to the robot and we programmed it to follow the light. So as we move this flashlight around, the robot follows. And I'm not going to show every example here, but we also have a demonstration where we attached a camera to the robot and we used it, we teleoperated it to access small and denied spaces. So here's our triangular robotic skins in action. We wrapped 20 of these skins around a passive 6-bar tensegrity and induced rolling locomotion entirely from the surface. So here's this passive tensegrity that's on the inside. And then we removed these skins. These are the same skins that were put on the tensegrity robot and just removed and now attached to a human instead. So this is a former postdoc of mine, Joran, and he's wearing the skins to create this posture shirt. The sensors in the skins are aligned along his back, and the sensor data shows when his slouching crosses a threshold, which triggers the actuators in the skins to begin pulsing to communicate that he should sit back up. So taken together, these demonstrations show how robotic skins can be easily transitioned between locomotion, manipulation, and wearable applications. So in sum, robotic skins are designed to be removable and transferable, so we can apply them from onto one object to perform a task, then remove them and apply them to a different object to perform a different task. The skins are also modular, meaning we can use individual skins to generate simple motions or combine them to achieve more complex motions and therefore more complex tasks. Ultimately, we designed the skins to be applied to, removed from, reoriented on, and transferred between objects so a user can create robots on the fly to accomplish variable tasks on demand. So in all of these previous examples, the robotic skins were wrapped around elastically deformable objects.
A current direction for this work is wrapping the skins around plastically deformable materials, such as clay-like materials. And this would allow the robot to change its shape to potentially adapt to changing tasks and environments without a human handler having to remove a skin and place it on a differently shaped body. So the idea is to use these robotic skins as surface sculptors, applying surface strains and pressures to mold the underlying body into different morphologies as needed. And we have some preliminary work towards this goal. So for example, here's a robot made from a robotic skin wrapped around a sphere of modeling compound. This is Model Magic, which is a clay-like material. And the skin contains pneumatic bladders. So when these pneumatic bladders sequentially inflate, it causes the system to roll. Now you can imagine scenarios where it might be useful for the robot to change its shape and gait. Let's say this robot approaches a small opening that it can't fit through in its ball configuration. This robot can apply radial pressure to morph from a ball to a log and switch from rolling locomotion to inchworm locomotion. And we applied a similar strategy in this robot, which uses a pneumatic body to switch between a cylindrical shape and a flattened shape. And the robot uses these different shape gait pairs to navigate both a flat and an inclined environment, demonstrating the concept of gaining environments through shape change. And here's another morphing robot, which employs both pneumatically driven and cable-driven skins to locomote and change shape. The robot is initially in a cylindrical shape and again uses sequential inflation of the bladders to roll forward. And upon encountering an obstacle, let me just start this video. Upon encountering an obstacle, it cinches in the middle, using its cable-driven skin to morph into a dumbbell shape and continue locomoting over the obstacle. So this demonstration shows how multiple robotic skins can be stacked as layers on a body and how an editable robot morphology can be used for obstacle avoidance, allowing the robot to change only its morphology while keeping the same path and control policy. Okay, so now I'm going to switch gears to talk about robotic fabrics. So fabrics are key materials for a variety of applications that require flexibility, breathability, small storage footprint, and low weight. While fabrics have conventionally been passive materials with static properties, recent progress in active fibers with actuation, sensing, and variable stiffness capabilities represent the opportunity to impart robotic function into fabrics. So in this part of my talk, I'll describe the functional fibers that we've developed in order to roboticize everyday fabrics as a platform for reconfigurable robots. So we've developed 3 functional fibers for robotic fabrics. The first is for actuation. We employ nitinol shape memory alloy wire. One challenge we encountered when integrating antagonistic wire bending actuators into fabric is that any off-center forces encourage the wire to twist in the fabric rather than purely bend. So this contortion can introduce chaotic actuation or even bending opposite the intended direction if the wire turns over within its couching, which is what we use to attach the SMA wire to the fabric. And we overcame this challenge by flattening the round SMA wire into ribbons, as shown here, to achieve controlled fabric bending. So this is a slightly different approach, but has a lot of commonalities with what Carmel presented earlier, using the SMA wire in elastic sheets. Both increase the aspect ratio of the actuator to control bending. So for the purpose of sensing, we developed a Pickering emulsion of PDMS particles coated in carbon black particles and suspended in an ethanol solvent. The Pickering emulsion is printable and results in deposition of conductive composite on the individual fabric fibers, creating resistive strain sensors suitable for state estimation and closed loop control while maintaining the fiber architecture of the fabric. So I'm going to talk about these in a little more depth. The Pickering emulsion is, these are kind of unique sensors due to their non-toxic fabrication process. So typically conductive composites need to be thinned with a compatible solvent, such as cyclohexane, which is what we use to manufacture the exfoliated graphite-based sensors that I talked about earlier. Here we use ethanol as the carrier solvent, which only suspends the Pickering emulsion particles. And upon deposition, the ethanol evaporates away and precure polymer particles spread out into a conductive film. So I just mentioned that typically conductive composites are made by thinning a precure polymer with conductive particles mixed in with a solvent, which is usually toxic. Here, because we're not thinning the precure polymer, but rather just suspending it in a non-viscous solvent, we can use a non-toxic solvent. So this means we can deposit the Pickering emulsion directly onto surfaces without damaging them. Using the more traditional approach of thinning precure conductive composite with a solvent, such as cyclohexane, it damages the underlying surface it's deposited on, which is evident here because it popped the balloon as it was being deposited. So this allows us to do some interesting things. For example, here we painted our Pickering emulsion ink directly onto the latex balloon inside a McKibben actuator, and we used the resulting sensor for closed loop control of the actuator. Since the sensor is now part of the actuator, we refer to this as a self-sensing McKibben actuator. And of particular benefit to robotic fabrics, this Pickering emulsion coats the individual fabric fibers without filling the space between them when printed into fabrics. So you can see confirmation of this in the bottom row of optical backlit images, where a neat fabric shows a porosity of about 5% and an inked fabric shows a porosity of about 3%. Compare this to a control conductive composite, which typically fills the fabric and removes any porosity. This maintained fabric porosity makes robotic fabrics particularly well suited to wearable applications where breathability is important for comfort. So here's one example where the Pickering emulsion ink is printed directly into a fabric. In this case, we use kinesiology tape, which was specifically designed to provide support to athletes without restricting their movements. The wearable sensor here is completely breathable and comfortable, and you can see the raw output data from the sensor during movement. And finally, just to show one more closed loop control demonstration, here you can see our Pickering emulsion sensors printed onto cotton fabric, and our shape memory alloy ribbons are actuating the fabric. So one sensor is printed on the top and one sensor is printed on the bottom. And we show closed loop control. The black line is the set point commanding the fabric to curve up and curve down, and the red and blue lines are the sensors on the top and the bottom of the fabric, respectively. Okay, and for the final functional fiber, for the purpose of variable stiffness, we developed this particulate composite made from low melting alloy particles in a thermoset epoxy, which displays a nearly 3 orders of magnitude change in modulus in response to thermal stimulus. So the Fields metal epoxy composite can be manufactured in fiber form and integrated into the fabric by couching, which is how we also integrate the SMA ribbons. By actively softening and stiffening the variable stiffness fibers, we can regulate the degree and direction of fabric actuation with higher repeatability and fewer total actuators. And an on-demand support structure allows the robotic fabric to perform move and hold operation or hold loads, which would otherwise collapse a typical fabric. So I think it's helpful to understand where we started with this work. When we were first beginning to think about variable stiffness, we started first with thermoplastics, then thermoset polymers, both of which are thermally responsive and change in stiffness via glass transition by about an order of magnitude. But an order of magnitude isn't actually that much, and we were looking for more extreme stiffness changes. So one idea we had is to incorporate phase-changing particles, such as low melting point alloy particles. Then when the material is cool and the particles are solid metal, the material should take on more solid metallic-like properties. And when warm, the particles are melted and the material should be significantly softer since it now contains liquid inclusions. So we set out to fabricate these low melting point alloy or melting point alloy particles, excuse me, specifically selecting Fields metal, which is a combination of indium, bismuth, and tin, and has a melting temperature of around 62 degrees Celsius. So here we sonicated Fields metal in heated water to break the Fields metal into particles, and then we cooled the dispersion while continuing to mix to prevent recoalescence of the particles prior to solidifying. And here you can see an SEM image of the resulting Fields metal particles. So mixing Fields metal particles into a thermoset epoxy had the desired effect. It increased the epoxy stiffness when cold due to the solid inclusions, and also decreased the epoxy stiffness when warm due to the Fields metal particles melting at 62 degrees and becoming liquid inclusions. The more Fields metal particles we put in, the more we broaden the stiffness range, but with the trade-off of embrittling the material in the cool state, and we find that about 46% by volume is ideal. The images on the right show both a neat epoxy sample and a Fields metal epoxy composite sample, both at room temperature. The composite sample holds twice as much weight with less deformation than the neat epoxy sample due to its increased stiffness in the cool state. So putting this into context with other variable stiffness work, we can see that the Fields metal epoxy composite performs pretty well. We compared it to purely melting materials, which perform similarly but need to be enclosed, and also to thermoplastics such as ABS and PLA, and to jamming technologies such as particle and layer jamming, and to human muscle. You can see that the stiffness range of the Fields metal epoxy outperforms most of these other materials and technologies. Its stiffness ranges from softer than latex rubber, noted by this dashed line right here, to about as hard as acrylic, as noted here, which is about a 3 order of magnitude stiffness range. On the right, you can see the same data plotted another way, just showing the ratio of stiffness change, which displays the same comparisons. And finally, we can fabricate the Fields metal epoxy into fibers by molding it in tubing and then sewing the fibers into fabric. So with the actuation, sensing, and variable stiffness fibers developed, we can now integrate these fibers into robotic fabrics. And we developed these 3 demonstrations. First, we demonstrate a shape-changing robotic fabric. The initial form is flat, and upon activation, the fabric softens and its variable stiffness frame lifts up to a table-like platform. The new shape becomes rigid and load-bearing, as demonstrated by weights being placed on the surface. And the shape is then returned to its initial flat configuration using an antagonistic ribbon actuator. And in the second demonstration, we show a robotic fabric tourniquet. So the tourniquet is a breathable fabric sleeve with embedded rows of parallel ribbon actuators, variable stiffness fibers, and conductive composite in-fabric sensors. When the fabric is cut along one of the sensors, the damage is detected as a broken circuit, and a compression response is triggered at the damaged site. The fabric compresses and then stiffens to hold that compressed position without further power supply. And finally, in this last demonstration, we have a self-deploying airplane wings in a fully untethered system. So this demonstration was inspired by the 1903 Wright Flyer, which also had fabric wings. The wings in our demonstration are seated into small slits on the side of the fuselage, where we put all the additional circuitry, microcontrollers, and batteries. The fabric wings curl to wrap around the fuselage for compact storage and uncurl into the deployed rigid state with the wings extended. This demonstration shows how a robotic fabric can self-stow when not in use and might be useful when low storage volume is required. So now I'm going to switch into the final topic, which is morphing limbs for amphibious locomotion. So this project is motivated by the challenge of traversing the shoreline. At the shoreline, there are 3 distinct environments: relatively stable open water, dry land, and the in-between, the surf zone. So efficient locomotion in each of these environments looks drastically different, and animals are typically optimized for either terrestrial or aquatic locomotion, but not both. Our concept is to leverage the related but distinct shapes of 2 groups of animals, sea turtles and land tortoises, to create a morphing limb which can transition from a flipper optimized for swimming in water to a leg optimized for walking on land. So as part of this effort, I'm going to first describe a fiber reinforced laminate material we developed for morphing capabilities. So this is an elastomer laminate with embedded inert unidirectional fibers, which results in anisotropic strain behavior. We added an adhesive layer to this anisotropic laminate so it can be adhered to the surface of any volumetrically expanding actuator to control its trajectory. So for example, in the images on the left, you can see an inflatable membrane. When the laminate is adhered to the top of the membrane, the strain limiting fibers induce upward bending. And when it's adhered to the bottom of the membrane, it bends downwards. So removing and reorienting the laminate on the surface of any inflatable actuator will allow the same actuator to be used to achieve multiple motion trajectories. So as you can see in this image, we use the laminate to control the morphing of our morphing limb prototype, which is visible on the surface of the limb. So the morphing limb is made of 4 primary components: fluidic actuators made from channels embedded in the elastomer, variable stiffness material, which is the same thermoset Fields metal epoxy used in the robotic fabrics, a flexible heater made from laser cut copper, and the anisotropic fibers composite used to direct the forces of the fluidic actuators. So this video shows a morphing limb sequence. The limb is neutrally in flipper state. We first apply a current to the embedded heater to warm the variable stiffness material, which softens it for morphing. Then we inflate, and the fluidic actuators morph the limb from the flat flipper state to a more rounded, load-bearing leg state. And the foot of the limb folds under for stable contact with the ground. We then hold pressure and allow the limb to cool and stiffen and lock in the leg geometry. Finally, when we reheat the limb again, it returns to its neutral flipper state. And attaching this morphing limb to a turtle robot platform results in amphibious locomotion with the limb morphology capable of adapting to both aquatic and terrestrial environments. So here you can see the aquatic and terrestrial modes as well as the transition. And here is the robot swimming. So these are preliminary tests. They're by no means perfect, but we tested both lift-based and drag-based propulsion strategies. The gates are not optimized. We're still working on fundamental challenges such as buoyancy control and wireless communication in multiple mediums, but you can get a sense here for the potential that this platform may have in not just achieving both aquatic and terrestrial locomotion, but as a means for studying the transition. And as an interesting note, we can use this platform to study 4-flipper aquatic locomotion, where sea turtles use 2 flippers and 2 hind rudders, but ancient plesiosaurs used 4 identically sized flippers. And like our platform, like our platform, but this is an understudied form of locomotion. Okay, so I'm going to wrap up here. In conclusion, my group is developing particulate and fibrous composites for next generation robots that will allow them to adapt their morphology, properties, and behavioral control policies to changing tasks and environments. And in this talk, I described several of these materials and their translation to several reconfigurable robot platforms. So I'd like to thank my students and postdocs, my funding sources, and thank you for your attention.
Thank you very much, Professor Kramer-Bottiglio, for this excellent talk and great work you presented. So we have already have a couple of questions, and let's start with the first. What is the force range achievable with robotic skins?
Oh, that's a great question. It's definitely not set. So it's dependent on the actuator. In our pneumatically driven robotic skins using McKibben actuators, I mean, they're linear contracting actuators, and it would be dependent on the scale of the McKibben fabricated. We also had the shape memory alloy driven robotic skins, which would have a drastically different force profile. So I would say it's completely dependent on the actuator choice and the scale. It's free for the designer to determine how much force they need for the body they're trying to deform.
Thank you. Another question that I have here is regarding where the person is alerted to improve posture. Could the sensors/actuators proactively correct the person's posture at a specific slouch position?
Yeah, that's a great question. In theory, yes, our actuators were not strong enough to do that. So our actuators were purely used as a means to communicate with the wearer. So when we had this kind of slouching threshold that was passed, detected by the sensors, our actuators just pulsed in order to tell the wearer that he was slouching. And I mean, I wore these skins. They kind of feel like a massage. They're definitely not producing enough force to actively pull the wearer back up. But certainly with, there's amazing work being done with new actuators. And I think in the future with stronger actuators, that would definitely be a possibility.
I see, thank you. I think the next question that I have, you partially answered it here, but can these actuators be used as a replacement for exoskeleton rehabilitation devices?
So these actuators, which actuators are we referring to? I guess just any embedded within the robotic skins?
Or the ones that you showed, the McKibben type actuators that you showed previously, probably muscles that you showed.
Yeah. So I mean, I covered, I guess, two types of actuators here. I mean, McKibben actuators. Carmel had a nice overview of McKibbens at the beginning of his talk. They've been around for a very long time, and I think they're extremely useful. And well characterized in the literature as to whether they could replace more traditional exoskeletons. I think I would almost defer that question to those who study that more explicitly. So there are entire research groups dedicated to developing soft exoskeletons and exosuits and adaptive exoskeletons, which is not something that we have explicitly studied. So in our wearable demonstrations, we have a couple. We had the robotic skins on the back as a posture shirt. We kind of speculated on the wearability of robotic fabrics in our reactive tourniquet demo, but we have not explicitly studied the actuators or either robotic skins or robotic fabrics in exoskeleton platforms.
Thank you very much. One question from me on this, on the great work on different vectors of the work that you've shown in this presentation. The compatibility between you said that actually it depends on the application at the end, right? What type of force you want, and then you can tailor this skin actuator couple, right? You can build whatever you want, engineer whatever you want, depending on what you need in the application. This is one approach. It's approach that you have an actuator and then you have a skin. Can you envision, or are you working on, or do you have any inputs on a system that will will be integrated, skin and actuator together? So something that already comprises a system.
Yeah, I think that's a great question. And it's something that we are currently thinking about. So our initial goal with this work is, as you kind of summarized, is creating completely robotic skins where the actuation, the sensing, we basically have a closed loop control or complete controllability of the movement of this planar material that can be wrapped around the surface of inert materials to turn them into robots. But certainly there's a possibility to then combine that with not inert materials. So to wrap robotic skins around systems that themselves actuate, and then try to use that combined actuation to do more interesting and more complex tasks. So that's not something that we have explicitly tested, but it's something that we're thinking about, especially with this goal of creating shape-changing robots, things that drastically change in their resting shape. It's a very challenging problem, and certainly having, kind of target pieces that would say, hey, this set of actuators is for task performance in one shape, and this set of actuators is for task performance in another shape, and then this set of actuators is just for going between those shapes. It's a really interesting area of research, trying to figure out how to reduce the actuator count while accomplishing all of these goals. And I think that what you mentioned here, this idea of using robotic skins wrapped around actuated bodies, is one potential solution.
Thank you very much. Thank you very much for your talk, your great research, and for taking these questions. We will move to our next speaker, and I'm pleased to invite Professor Stephan Rudykh from the University of Wisconsin-Madison in the United States to give a talk on tailored design of soft materials through microstructures and buckling. Please, Professor Rudykh.
Hi, Aslan. How are you?
I'm good.
Very good to see you. And thanks again for organizing this and for inviting me. Really, a good thing to do something with other people outside. So, and one more thing for not turning off your camera, otherwise it would look like my course when I don't see the students entirely, just talking to my screen without any feedback. So please stay if you can. All right. So. This talk will be, I guess, somewhat different in spirit from what we have seen before, but I'm actually glad to follow up on these nice videos and very inspiring motivation and interaction, how soft materials can be used. So what I'm going to do here, so in the interest is, and to look into inside the material with the microstructures and understand how these microstructures form and what drives this formation of different patterns in soft materials. And we are focusing, we're trying to answer the question how these materials fail, and when they fail, what actually happens and how we can use that maybe for our benefit. And also the influence of different fields, magnetic field or electric field, as we try to actuate these materials. But here I will just focus on the mechanical part of that, so on the mechanical force present without to complicate this too much. So here is just a few pictures of the examples of what we'll be going through. Just first start from a relatively simple system of laminates, how buckling of stiffer layers give rise to different patterns, and just a matter of introducing the instability phenomena in the soft materials, and then I'll move on to 3D fiber composites, and then going back to 2D systems with a somewhat more interesting behaviors that we can exert there, and that's where I put a name of metamaterials here. But okay, so I don't want to confuse anybody, so just a fancy name for relatively simple microstructures that that produce nice figures out of something simple. But all right, so let's just start from the simplest example that I could think about for composites is periodic laminates, and so what you're looking at now, I hope that the picture goes through enough to see the grayish area here, which is a matrix. It's a 3D printed material. Okay, so and the dark area here is a stiffer layer, and so the ratio between the stiffnesses is not very high, so it's on the of order 20. And so now we're going to compress it in the direction of these layers. And as you expect, very similar to Euler buckling. So this at certain strain, this stiffer layer will buckle. And the wavelengths to which they develop will be regulated by the surrounding matrix, because, well, now they need to somehow communicate to each other and they decide what they will do together. So just to illustrate the geometrical changes that will happen if we increase the volume fraction of stiffer phase. So this is the ratio in the geometrical thicknesses here. And you can see that then what happens is the wavelength will change. So we have this geometrical parameter first that regulates what we can exert upon instability, and also we can change the material. And now, so we printed here the stiffer layer being much stiffer than the matrix, so more than 1000 in contrast, and that allows us to travel to this what is called long wave type of instability, and of course the strain at which the composite buckles is significantly smaller than in this relatively soft composites. And again, so the material have enough elasticity, don't dissipate too much energy. So when we release the loading, so you can obtain the initial state of the material. So this is a reversible type of transformation in soft materials. Again, limitation for the reversibility will be in the material itself, as it will fail catastrophically or not, and that also possible. Right, so I don't have too many nice videos, so that's things are moving. So I need to live up to the previous presentations, and so I'm not sure if that goes well here or not. So, but this is this video taken from the experiments, from simple experiment of compressing this all right, it seems that it may not be working very properly. All right, so the whole point was to illustrate this, the deformation of the wavy pattern. It was, of course, supposed to be much smoother than probably the computer. The Zoom translation takes too much resources from my computer. And so, and the deformation of these wavy patterns can be very nicely predicted theoretically, and that's where our focus on, and also through numerics. And I will, so typically we write lots of equations, and I'll just compress it to mostly this slide, so will be relieved after that, so we can continue without going very deep into the equation. So the analysis is just in the 2 sentences is, typically, you use what is called block-Floquet analysis that allows you to scan through scanning different wave numbers and satisfying certain conditions to identify the instability at this wavelength scale. And as a limiting case of that, you can look into the homogenized response of the material and the effective properties of that, and that allows you to look into this. What is called long wave type of instability can be detected relatively easily if you know the effective moduli of this material. So they can compose it into this tensor of elastic moduli. And so in this way, in other, you get the information what happens at the initiation of instability, and then you can go into the post-buckling regime and give this information to, say, finite element that typically used for that, and then you can go and see what happens after the buckling happens, how that develops. And typically what to expect, again, on this simple example of the laminate, is that in terms of your stress-strain behavior, you expect upon the critical strain, I expect the material to go into softer mode of deformation. So that's where the material seeks to go into low energy states. And that's where also these imperfections that we put here start to grow very fast. And that is the manifestation of developing instabilities after the onset of buckling. And so with this system, again, very simple. So we had, as I mentioned, two parameters that regulate the instability patterns that will emerge after that is the geometry, or let's put the thickness ratio, volume fraction, and the contrast in the material properties, or stiffness contrast of the layers and the matrix in the beginning. And so once you specify that, you basically land here one particular and unique pattern that you can trigger. And so for us, it would be interesting to find a way to actually be able to travel between these microstructures for a given, say, printed material in the beginning. And one of the ways that is just explore, basically use what soft materials offer is their inelasticity. And here is just one of the examples using their rate dependent or rate sensitivity. I'm going to illustrate that next on a simple, again, so continue talking about laminates on a simple example of the same 3D printed laminate that we load relatively slow. This is strain rate here, and relatively fast, but still in a quasi-statical manner. So it takes the same sample and load it faster here and slower here, and you can see that this is already brought to the same level of deformation, that the ones that exert the viscoelasticity of the stiffer layer already developed the buckling, while the ones that we loaded slowly, they didn't didn't trigger viscoelastic responses from the stiffer layer, still stable. So of course, we can also model that with the right fitting parameters. And if you take many of them, so enough of these parameters probably can fit anything. So that should come with no surprise. Just next, we'll show that, of course, if we continue loading to highest strain level, so the one here also will develop, the one that loaded slowly also will develop wave pattern, but the amplitude is not that high, and here we already have a very well developed pattern. So basically the same material loaded exactly to the same state, just the history of loading that led to this difference for this. And so from 2D to 3D, now for fiber composites, we can use this approach of this loss ellipticity analysis, and then we can derive the critical deformation level, critical stretch, at which the material will buckle in this compact form. And these moduli here, based on the micromechanics of the material, basically all of them have the information about the amount of the material and the property of the fibers and the matrix. Now, putting that into comparison with laminates, which is much easier to deal with from a theoretical point of view, or from modeling, and therefore they could be used for estimating the stability of fiber composites. Now I'm going to compare that to this, the map that the curve basically divides the regions where the material is stable. So we have fiber volume fraction here on the x-axis and critical stretch here. So when it's unit or 1, the material is undeformed. So then you start to compress. That's where it decreases, and then you meet this curve here, and that's where we predict the material to become unstable. This is the curve derived for the analysis that corresponds to long wave type mode. And So we also can allow these laminates to deform in 3D, and that's how the curve would look like. And then we're going to compare it to fiber composites. So that is the prediction here. So what we would see from these pictures is that for whatever reason, for small volume fraction, material is extremely stable, right? So then you need to deform it quite a lot before you get to any instability or buckling of these stiff layers or fibers. And this, of course, is not reasonable, as the fibers will even isolated fibers will buckle there quite soon. And therefore, the full analysis is needed here. So in that or microscopic instability analysis, it's using the Bloch-Floquet analysis when we scan different wave numbers. Then that nicely predicts this appearance of these instabilities also for laminates and for fibers. And for fibers, there is an interesting indication that maybe we'll be able to develop helical-like structures. And so, so this is again to answer the question what is the critical strain or what the critical stretch, basically answering when the buckling happens. And the next is show the information on actually what happens at the microstructures length scales. So we are looking into the wave number, critical wave number that says at which wavelengths the pattern will develop. So this for laminates, again, in 2D and 3D, and of course, it's the same material, just allowed to deform a little bit differently, so the same wavelengths of the pattern develop. And now with fiber composites, there are quite significant differences that are predicted. So the factor, for example, here can be 8 or some very significant difference in the wavelengths at where they develop instabilities. And again, so you can just to illustrate that as we decrease the volume fraction, the wave number increases, or wavelengths, because it's inverse of that, will decrease. And at certain situation, we also start observing numeric some strange helical structures in 3D emerging from these fiber composites. Now, so with that, we try to find similar behavior in experiments. So this is an experimental results for these fiber composites, and that's very typical behavior again. So of these curves. So upon buckling, you have that softening behavior. This peak indicates where the instability developed. Also, we cannot really say precisely when it happens until you use some visual means, but this way or another, these points can be taken, so you can detect these critical strains and then put them here as a, well, together with the numerical curve, you can put them as the the curve or as a function of fiber volume fraction. And you can see that again, so the trend here captured quite accurately, and that was very encouraging. Now, for again, a similar question of what happens at these levels, at these systems. So we're looking into this critical wave number and starting from the numerical prediction. And then for the fibers, in fact, we were able to capture this transition that is predicted numerically and theoretically from the long wave type of instability into the certain volume fraction, into the microscopic type of instability. So, and well, the pictures are not great here for reasons that taking the pictures of the fibers, it's not the laminate. So we're basically taking the picture through the transparent matrix, so to see what fibers are doing here. So again, the transition is captured. That made us very happy. Also, of course, if you try to capture, to compare the differences in the wave number, there will be quite significant differences in what is predicted in the simplified material models versus actual observations in the material, in the experiments. And in the attempt to regulate these instabilities, control these patterns. And once again, if we control these patterns, so we control the properties of the materials and can exert interesting behavior, especially in the unstable or nearly unstable regime. So then here to control the instability, we basically play with the arrangement of the fibers and putting them closer in one direction than the other. And through the playing with this aspect ratio, say, or positioning fibers again closer in that direction in the other, so we can tune these wave numbers, so therefore the pattern by a factor of 5, also with quite large aspect ratios. And in fact, what is interesting for that, for certain behaviors, certain geometries and material properties, the fibers start to do something that is counterintuitive when they buckle. So when they collectively buckle in the stiff direction, while one would think that they would prefer to go and buckle in the soft direction when there are lots of metrics with that. So there is an explanation for why it happens, but that requires a little bit going into details of the analysis behind this and showing the polarization, how they evolve with the deformation. So not going into that depth and just illustrating that that's indeed what happens in experiments when we test this configuration with these material properties. And again, the trend is captured very nicely. Also, of course, the difference in the actual critical wave numbers can be rather significant here. So here may be better that if you compare these two, there will be quite significant difference. All right, so this with simple examples of fibers and laminates. Now I'm going back to 2D, and all right, so this is where I hope that my video will work. All right, so because it's essential. And so here's the view of these auxetic materials. We have basically three phases here. So the grayish area here, these are stiff inclusions, and that helps to regulate the pattern. So there is a dark areas here. This is a actual rubbery material that where the whole process happens. All the deformation happens in this. All right, so I need to be quick here, I think. So, and the white part is the voids that collapse. And basically, if we will be able to go into the beginning of the video, you will see that there is some, at the beginning, there is some chirality-like structure that form, and then you continue to break that, and basically by positioning these stiff inclusions, so you can regulate what will happen here. Now, so one of the things that you'll of course notice is that because we have these voids, and this is but there's no surprise in that that the material will exhibit the auxetic behavior, because we have some possibility to change the volume. So you compress in this direction, but it doesn't really expand in the other. And well, schematically put it in here, so okay, antiformed and deformed state. Now we can define something similar to, let's call it Poisson ratio. So it's not exactly that, but just to some measure of changing in the volume. And you can see that in the beginning, this is close to what is expected of soft materials. So typically, soft materials are rather incompressible, given the Poisson ratio of 0.5. And then here that we indicate the critical strain, the dashed line, then that's where the collapse of the voids happens, and that's where we rapidly going into the negative Poisson ratio regime, or just decreasing that. And you can, with strain, you can regulate where you are. So, for example, you may not really be you're not interested in publishing that with some fancy words and negative auxetics. It's just for engineering application, need negative, you need Poisson ratio actually being 0, right? So you compress it, but it doesn't really try to deform in the other direction, so that you can regulate it by the strain and at a certain level. Another interesting notion with these materials is that upon this development of these instabilities, you can open, and we're not talking much about here about the propagation of elastic waves in these materials, but when material goes into this unstable regime, there are some interesting behaviors that develop here. And one of these is the opening of the band gap at low frequency. And when I say band gap, I mean a frequency range where waves cannot propagate. So effectively, you create a filter. You need to say, of course, with this material, there are lots of band gaps, of course, always exist without any deformation. You don't need instability to go there. It's just they will be at a higher frequencies. And there for you, typically challenge is to open band gaps at low frequency, so you can create a reasonable size of microstructure and put it on the wall or on the window and filter noise. For example, that is an application for that. And so, and that may be related to the auxetic behavior, because that's where you can probably manipulate the pressure waves that are typically not that easy to control with soft materials. Right, so so one more example of some understanding that comes from the consideration of simple laminates is this hexagonal network system. So again, embedded in soft matrix, and here we again have let's parameterize that with the geometrical parameters, a ratio of the thicknesses of the say matrix here and the network thickness. And so then upon loading this, we also can expect the buckling of this network. Now, with changing the geometrical parameters of the thickness ratio and stiffness, we can pre-design these wavelengths here. And so with that, I'm going to show these examples. So we can choose a thickness. Let's say we have the materials are fixed, so we printed. We just have two materials that we can print with. And so then we just play with the geometry, and then we can choose a thickness such that there will be enough wavelengths here, more than one, two, and that what we expect to go. Okay, so this is a nice picture, and then it becomes even more interesting when we can match the length of this unit cell with the one wavelength. So again, by changing the thickness. So that, and then you can go on and just change the thickness such that you will have exactly half wavelengths in that unit cell. That's what you obtain. But then if you start to increase it even more, so that then some interesting patterns start to emerge here, and they're somewhat similar to what is observed in information in biological tissues during the growth process. But of course, that process is by far more complicated and include not only the elasticity, but many other parameters here as well. And so again, going back from mentioned biological materials. So basically, we like with laminates, we have this map of geometrical parameters and material stiffnesses, so we can pre-design the patterns and the properties of the materials that we can switch by deformation or by other fields that we apply, and make material go into this new configuration on the microstructure level. And with this also, we can open these band gaps, and that's typically what you will see in the in consideration of elastic waves. So I'm not going into details in this dispersion curves, indeed, just showing that once we deform the material and force it to go into the buckling state, so unsimilar to different from the undeformed state, so we have a range of frequencies where the waves are prohibited and cannot propagate at all. And the interesting notion what would happen here, I probably need to skip this to just say that there is an interesting behavior of emerging negative group velocity of these waves trying to propagate through this material. This is an example of that simple poor laminate. And in fact, it doesn't really need the material doesn't need to be rearranged to the buckled new geometry. It can be brought near to that state, and that's where the this negative group velocity will appear. Just okay, another negative negative property in addition to the exotic negative Poisson ratio. This is something that also can help to design the material with left-handed behavior. So when the waves propagates at an unusual angle when it meets with the interface of such material. And so basically you can bring the material close to the instability. So visually nothing will change, the geometry will be the same, but the material will feel that there is something funny going on at this wavelength. So it's ready to buckle, but not yet. And so this is how these eigenmodes are changing from the undeformed to the slightly deformed, but still stable material that here. So, and therefore the material start to behave and show unusual properties. So what I'm trying to emphasize here, that's not only the geometrical changes that you need to get this unusual behavior, but actually the whole phenomenon behind this is important. Otherwise, we would just can print particular geometries that we need and can obtain these properties, which is in fact is true for the exotic material. So there, the phenomenon of instability is not important, but rather the geometry itself is defining the factors. And then finally, this an interesting example of new type of instabilities that we found in this in the soft composites. And here again on the example of particulate structures, and here the white dots are stiffer inclusions embedded in soft matrix. I'm going to compress it, and it's quite a frustrated system already. So then these inclusions will need to rearrange, and they do, but maybe harder to see it without help. So that's where these dashed lines are very helpful. And so you can see that the material is rearranging into let's call it some antisymmetric domains or twinning patterns. And the interesting thing about it is that the analysis would predict here the long wave for macroscopic instability. However, very clearly here, this microstructure shows that we have highly regulated at certain wavelengths comparable with the microstructure side. New microstructures that form upon that. This, in fact, so can some change in the geometry showing that just not particular one way it happens, but also different geometries of similar composites. And so, yeah, we can quantify that domains by, say, angle of these new domains. Of course, they were zero, the orientation angle at the beginning. So upon instability, they merge. Can track that. And finally, I don't have any time, I guess, so I need to apologize. Probably already late in. Are you in Zurich, Aslan? All right. Okay, so that will be very last slide. So they're just finishing here. So just trying to explain, maybe give some initial thoughts about why this new instability formed here. Is that so if we start from this system of single column of inclusion and then we compress it, so we can expect something similar to laminate to happen here, because they can think about this region as a collection. It's effectively a reinforced laminate, right? So we put the inclusion and put the stiffer layer here effectively. And so that's indeed what will happen. And then now as we start to transition from here to here, we put these, say, layers closer to each other, and that's where they, at certain point, will start to communicate and need to find a new microstructure to develop. So in this case, the wavelengths doesn't change because they are not close enough, but if we bring them close enough, then they need to communicate and they need to decide collectively how to buckle so they can minimize the energy. And the wavelength changes as we go from here to here. And in this case, they're already too close. They cannot develop this wavy pattern. And so that's the way where they need to find a new configurations that are different from the wavy pattern here to the classical one. And of course, that also indicates, because this transition is not sudden, so we can gradually change the relative position of these columns, and gradually will get to this the wavelengths that will be comparable from what we started with from single column. So it's definitely not a long wave type of instability. So just and that will be all. Thank you again for listening. And that, I believe, was quite different from the previous talks. Were more of actuation. Here. Thank you, Aslan.
Thank you very much, Professor Rudykh, for this great talk. While the audience prepares their questions, I have one probably conceptual question to you. You showed the modeling and then the experimental output of the very interesting behavior of different patterns that you can get as a response to, for instance, pressing, right? As you showed previously, it's compression. Now, how do you envision it conceptually? In it's passing, right? You press with something, right? You use the instrument, you use something to press. Now, how do you envision these patterns being used in skins that Professor Kramer-Bottiglio talked about before, or in actuation materials or skin actuation composites? Can you shed light on your perspective on this? Can it be useful in this application?
I think that the closest one, well, besides the fundamental understanding of what this soft composite helps, I think this the most useful insight, so closest to using this material, that could be the material, the exotic material that can change their volume, right? You can envision a soft robot that can go into tight space, and then after going through that tight space, can regain the whole shape. And also, this is a mechanical type of deformation that I show here, but this is basically just the first steps in understanding what happens there and how we can design it or pre-design it geometrically. And there is a line of research in my group when we do the same by applying external fields, electric field or magnetic field, to exert, without touching this material, to exert all these changes in the form and shape. So, well, others maybe will require more thoughts how they can be used. Or we applied some of this to cable-driven actuators by putting different fibers and pre-designing the response of the composite. And design some soft grippers with that. So some that can be more directly used. Some kind of, okay, it's more fundamental understanding. It would be too stretched to apply it directly immediately to some actuators.
Yeah, thank you very much. We got a question from the audience. It says, thank you for the talk. Programmable design is interesting in soft robotics. Could you comment about the effects of these instabilities on macroscopic properties of the composites? Macroscopic properties of the composites.
Well, so there can be two parts in that. So first, let's say you want to design, you still use your soft composites, say some fiber composites, to have the that was actually applied for designing a different actuator, so you can induce some directionality and tailor the performance of that. So, for example, so you may want to actually avoid these instabilities and work in a safe regime for that. So, then you don't need to know much about what happens after. You just need to know when it happens and avoid this situation by pre-design, knowing what deformation your material or actuator will need to undergo. And then you can change the geometry inside the material to change that. On the other hand, if you want, or for whatever reason you want to go into that post-buckling regime, then you can add different functions into the material that could change, for example, the properties of the material. Typically, that will be pre-designed softening if you go into post-buckling, if that's what you would need. I know maybe for touching some delicate objects that you would want the material become softer, and then also can regain the rigidity if the larger forces that need to be exerted on other objects. But I believe there are other systems that may be more suitable and less complicated for that, as again, these magneto-active materials, when you can apply magnetic field and make it stiffer if you like. So they're probably, again, I need to well, I agree here with the previous speaker, so it's design oriented. There probably will be a large pool of materials with different behavior, this one with switchable behavior, and whether that is needed for particular design or not, that's up to the designer. And I think for me, there are quite many fundamental questions, just curiosity-driven research in some parts of that.
Thank you very much. So thank you very much, Professor Rudykh, for your great talk and for taking these questions. And I would like to thank our speakers for their outstanding contribution to this session. Now we've done with all the talks, and special thanks to all the participants for their time and curiosity about soft and biohybrid actuation. Your excellent questions contributed a lot to the spirit of the discussion. By attending this session, you have contributed to creating a community, soft and biohybrid actuation community, which is the base for creating more dissemination events on the topic. This was the first event of its kind, the first online conference fully dedicated to actuation, which will continue till November 27th, and the first online session, this session, fully focused on soft and biohybrid actuation. I am committed to advancing the soft and biohybrid actuation research, and I'm looking forward to the next event for the soft and biohybrid actuation community. And I would like to thank you very much. Thank you all. Thank you very much.
Thank you, Aslan. Thank you for organizing this. Really great job. Thank you.
Thank you.
Thanks, Aslan.
Thank you all for your time.